A very good morning to all. On behalf of Electrical Engineering, NIT Silchar, I welcome you all for the third day of 5 days workshop on advancements in electrical engineering and industrial and academic approach. So today we have our guest, Dr. Vijay Kumar Krishnasamy sir from IIT DM Kanchipuram. Just before going into the session, let me give a brief intro about our speaker today. Dr. Vijay Kumar Krishnasamy obtained his bachelor's degree from Coimbatore Institute of Technology, Coimbatore in 2006. He obtained his MTech in Power Systems in 2009 from NIT Trichy and PhD in Electrical and Electronics Engineering from NIT Trichy in 2012. He completed his postdoctoral research fellowship in NTU Singapore in 2013. Presently, he is working as Assistant Professor, Department of ECE, IIT DM Kanchipuram. Before joining IIT DM, he worked as Assistant Professor in Department of EEE, MNIT Jaipur for 5 years. He is a visiting professor in University of Saskatchewan, Canada. He has published more than 40 papers in peer-reviewed international journals and conferences. This includes a number of IEEE transactions, IET, elsewhere, etc. He has a number of funded projects from government agencies, approx 1.3 crores. He has guided a number of PhD students. He is a reviewer in SERV DST project proposal and DST. He is a reviewer in IEEE, IET, elsewhere, Sprincher, and a lot of other journals. And he has obtained a lot of awards and recognitions such as visiting professor in University of Saskatchewan, Canada, Shastri Indo-Canadian Fellowship, IEA Young Engineer Awards 2017-18, visiting researcher in Alexander University of Germany, Young Faculty Fellowship by MHRD, Young Scientist Award for Startup Research Grant by SCRB, Posoko Power System Award for doctoral thesis, and listed up top 10 among all IITs and NITs for his PhD thesis. And he is selected for Canadian Commonwealth Research Fellowship in University of Saskatchewan, postdoctoral fellowship from NTU, MHRD fellowship for both PhD as well as MTech. It's a real privilege to have you with us, sir. Now let me request the guest speaker, Dr. Vijay Kumar Krishnasamy sir, to take over the session. Sir?
Sir, yeah, thank you a lot, sir. And thanks for the invitation to give me an opportunity to present my work in this workshop. At the same time, I'd like to thank the another coordinator of this program also and your institute for the invitation. It's my great privilege to be presenter in this certain training program. Today I'm going to talk about power electronic controllers for wind energy.
Sir, Vijay Kumar, sir. Yes, sir, can you put in presentation mode, sir? I think it's not in presentation mode.
I mean, you need a full screen?
Yeah, sir, full screen mode, sir.
Yeah, sure. I will make it. After introduction, I thought, okay, I can set to that.
Okay, sir. Thank you, sir.
Yeah, sure. So today, I'm going to discuss about the application of power electronic controllers for wind energy conversion system. In previous lectures, you may heard about the basics about power electronic converters and the application of the converters for different scenarios. So here today, just we are going to talk about the wind energy conversion system. So before jumping into the power electronic controllers, I would like to give some brief introduction about the wind energy conversion system. So before going to the wind energy conversion system, we are in the mode of energy transformation. So as per energy transformation by 2050, the main objective of this energy transformation is to reduce the carbon emissions. So what they are focusing is, at least they have to reduce this carbon emissions 70% as compared to the today's level. So that's what it's the guidelines proposed by the IRNA. So in this, one of the major key point in the energy transformation is to incorporate the renewable power generation units. So by having the renewable energy power generation units, you can able to reduce the electricity cost. So here, when we come into the energy cost, it almost you can say the electricity cost from this renewable power generation is reducing significantly now. So with that, if you are spending $1, you can get the $3 to $7 as a payback. So that's what, in terms of economic point of view, we can say it's a benefit to all people. So at the same time, when we come into the security, even we are having the conventional power plants. For this conventional power plants, we need a fossil fuels like coal and oil. So these fossil fuels are imported from the developed countries. So once is there any issue with this supply chain, then we'll be in the crisis of energy. So for that, if you are having the renewable power generation, so we can able to improve our energy security for our nation. So currently, just almost 64% of the fossil fuels are imported from the other nations. At the same time, you can say the full energy access. So once if you say the development of the nation, it's depending upon the even you can say the energy demand is a part of the growth of the country. So we can say if you want to be a developed country, then all people need to access the energy without any interruptions. So by having the renewable power generation sources, so we can able to give the power supply to the rural areas or remote areas, as well as this distribution power generation sources also distributed in our network, so we can able to reduce the transmission and distribution losses. So that's another major advantage by having the renewable power generation sources. Another aspect is socio-economic point of view. So by having this renewable power generation, we can able to create a lot of jobs. So even we can see now this photovoltaic panel installation and the photovoltaic system power generation, it creates a lot of job in our country also. So this is what just I want to convey with the energy transformation by 2050. So the estimation for renewable energy generation is 86% in 2050. So in this 86% of the renewable energy generation, then almost if you look into it, 1/3 of the power, 1/3 of the power is generated from the wind power plants. So more than 1/3 will be from photovoltaic power generation unit. So that's what this diagram gives. So that's what it's a estimation given by the IRENA. So just if you want to very detailed about this policy guidelines, please you can visit this website. So when we come into the wind energy conversion system, so these are the major key milestones in wind industry. So 1982, they have started with the 22 kilowatt capacity of the wind turbine, that too with the 3-bladed system. Then 2001, they have come up with the 1 megawatt rating of the single turbine. So here, whatever the rating we are given here, it's for single unit. So in 2001, they have come up with the 1 megawatt of the single unit wind turbine. So at the same time, if you look at 2008, in 2008, we have generated almost 100 gigawatt of the power from the wind turbines. So at the same time, within a decade, if you look at 2018, almost 5 times of the power is generated from the wind turbines. So that's what we can say the global installed capacity, it's 564 gigawatt. So within a decade, just we have increased the installed capacity of the wind turbines to five times. At the same time, if you look at recent development in the wind industry, they are having the 10 megawatt of the single commercial wind turbines are available in the sites. So that's a development. Even just we can have the single unit of the wind turbine with a capacity of 10 megawatt. So earlier cases, they have come up with 100 kilowatt, 200 kilowatt till 5 megawatt of the wind turbines. So now they have developed the single unit with a capacity of 10 megawatt. So this is the some statistical points. So if you look at the 2010, only 1.7% of the power is generated from the wind. So in 2050, they are expecting more than you can say so more than 1/3 of the power should come from the wind energy conversion system. So that's what they are given the roadmap for wind power generation. So as of now, the installed capacity, if you have seen the 2018, the installed capacity is almost around 565 gigawatt. So out of which 542 gigawatt is coming from the onshore wind turbine. So whatever the wind turbines, it's located in onshore. So from the offshore, just we are having only the 23 gigawatt. But when we look into the forecast, so they want to improve the offshore wind power generation drastically to 1,000 gigawatt by 2050. So there is a lot of progress that's happening in the offshore wind turbine. The reason behind is if you are going with the offshore wind turbines, the maintenance is less. At the same time, you will get the huge wind velocity, so that we can go with the higher capacity of the wind turbines in offshore. So that's what they are preferring the offshores for installing the wind turbines. And if we have look at the annual deployment of the wind energy conversion system, it's onshore. Just it's going 45 gigawatt per year. So every year it's keep on increasing. At the same time, just if you look at that, offshore wind turbine installation is less, but in future we can look at the large number of installation in the offshore. So this is the case in the renewable energy in India. So as of now, 87 gigawatt of the power is coming from the renewable power generation sources, including photovoltaic, biomass, small hydro, and all. And they are expecting that by 2022, they have given the target that the installed capacity of the renewable power generation is 175 gigawatt. So for achieving this, the government is giving a lot of schemes and subsidies for installation of the wind turbines as well as PV systems. So if you look at the installed capacity with different renewable energy sources, almost 37% of the power is generated by the wind turbines. If you look at the solar PV system, it's a 34%. But by considering the compatibility of the photovoltaic systems, in next 5 years, we can expect that the installed capacity may overcome the total installed capacity of the wind energy conversion systems. That's what nowadays there are a lot of schemes given by the government. Even the solar parks and all in the buildings as well as barren lands. So by having that, the solar PV can overcome this wind in the coming 5 years. So if you look at the key trends, these are the total electricity generation from the renewable energy sources. So if you look at the progress in every year, it's keep on increasing. In 19 and 20, only you can say it's only 1 billion unit is varying, but due to the economic condition of the country, we are standing at this point. Maybe in future we'll be in the progress mode. So when we come into the wind energy conversion system, just we are having the single wind turbine. The wind turbine, when we talk about the wind turbines, the capacity of the wind turbine will vary from some few kilowatts to few megawatts. So here there are two types of wind turbines. One is horizontal axis wind turbine and another one is vertical axis wind turbine. So earlier days they have used the vertical axis wind turbine. So here the problem is mechanical stability issues as well as structural issues during the gusty wind speeds. So that's what they have moved to the horizontal axis wind turbines. So this horizontal axis wind turbines will give the good mechanical stability. Here the generators and power electronic controllers may located on the top of the tower, but here the generators are located on the bottom of the wind turbines. But commercially, when we look into the commercial applications, they will prefer the horizontal axis wind turbines. So these are the different types of components which are available in the horizontal axis wind turbine. So when we look at this diagram, here on the front, just we are having the rotors. In a rotor, just we are having the blades. So the number of blades in wind turbines are 3. So do you know the reason behind to select the 3-blade system? So normally 3-blade system means it's a odd number. So they will prefer to have the odd number of blades in this rotor. The reason being is you can able to extract the energy from the wind in higher. So if you are having the even number of blades, even you can go with 2 number of blades or 4 number of blades. The another disadvantage with the even number of blade is at the one point of time, so your one blade is in the bottom of your tower and another blade on the top of your tower. So during the at that particular point of time, what will happen? The top blade, the top plate will face the higher wind velocity, and the bottom plate will face only the less amount of wind velocity on the blade. The reason behind to get a low wind velocity at the lower blade is because you are having the tower here. So that tower can give the shading effect to the lower blade. So that's what just you will get the mechanical instability in this even number of blades. So that's what they won't prefer the even number of blades for the wind turbine application. So people may ask that instead of 3, why not 4? Why not 5? So 4 is not possible because that's what I told you. Even number of blades you won't prefer. So why not 5? So yeah, you can go with a 5 number of blades. Again, the problem is if you are going with a 5 number of blades, the cost of the system will increase. Why? Because the single blade itself, it will cost you almost 2% of your entire wind turbine cost. So if you are going with a more number of blades, the cost of the system will increase. At the same time, if you are increasing the number of blades, the speed of the turbine also will reduce. So even if you look at the 2 number of blades and 5 number of blades, there is a huge difference in the speed. So do you have any idea about the speed of the wind turbine in real time? The speed of the wind turbine in real time is up to 10 to 50 RPM. So 10 to 50 RPM. So if you are going with a more number of blades, again the speed range will come down. If the speed range comes down, then the gearbox stages will increase. So again, if you're by increasing the number of blades, again the cost is increasing with the number of blades. At the same time, if you are increasing the gearbox stages also, again the cost will go up. So adding together, the entire cost of the system will be higher. So that's what they won't prefer the more number of blades in the wind turbine system. So that's what for trading off the cost and the gearbox stages and all, just they have come up with the 3-blade system in a wind turbine. So that's what even if you look at wind turbines, just we are having the 3 number of blades. Here, these blades are connected in the hub. So here, this rotor is connected with the low speed shaft. Why I'm saying low speed shaft means here the wind turbine speed is lower. You can say it's a 50. I can say 50 RPM. So here, this low speed shaft is connected to the generator through gearbox. So why we need to use gearbox here means, so I can consider our 50 hertz power supply system. For 50 hertz power supply system, by considering the 4 number of poles in the generator, so your synchronous speed of the generator is 1500 RPM. So here, for generating the power, you have to rotate this generator at 1500 RPM. But here in the low speed shaft, what's my speed? It's a 50 RPM. So just you have to match this 50 RPM with the 1500 RPM generator speed. So for that, we need to use the gearboxes here. So this gearbox cost is higher in wind turbines. So that's what nowadays people are working on, gearless wind turbines. So here the generator. So when we come into the generator, is an electrical machine. So we can use different types of generators like induction machines, slip ring induction machines, permanent magnet synchronous machines also can be employed commercially in the wind turbines. So here, apart from this generator, we are having the anemometer and wind van here. So this entire part on the top of the tower, just we are having this part. So this part is called naturally. So in the naturally, just we are having the gearboxes, generator, anemometer, wind van. In addition to that, just we are having the brakes, mechanical brake here. So this mechanical brake is connected in the high-speed shaft. And if you look at the anemometers, these anemometers are used for measuring the wind velocity. So why we need to measure the wind velocity means, in some turbines, we are having some control algorithms. So for that, we need to give the wind velocity, or you can say the wind speed as a feedback. In addition to give the feedback to the control system, just we need to stall the wind turbines during the gusty wind speed. So whenever just you are having the windstorm, during that time, just you have to stall your turbines. So for that, we can use the feedback from the wind velocity feedback from the anemometer. And wind van. So the purpose of the wind van is to measure the wind direction. So why we need to measure the wind direction means, when we go into the location, so there is a variation in the wind direction. So you won't get the wind in the same direction. So the wind will keep on change. So by having the wind van, you can able to measure the wind direction. So according to the wind direction, you can able to rotate the naturally to face the wind. So whatever the wind direction, you can able to rotate this entire part. Entire part means it's naturally. So we can rotate this naturally to face the wind. So for rotating this naturally, you are having the yard drive system in between your tower and the naturally. So here you are giving the feedback from the wind van to the yard drive. So this yard drive can able to rotate this naturally. So whatever the wind direction, you can able to rotate this naturally to face the wind. So this is the and in that, the bottom of this yard drive, just we are having the tower with a height of 100 meter. They will prefer to have the tower height above 60 meters to 100 meters. The reason being is, if you are having the lower height of the tower, you cannot able to harvest the energy from the wind. The reason being is, just we are having the buildings as well as trees, so that will give the shading to the wind. So that's what they prefer to install the wind turbine above 60 meters height. Okay, so when we come into the cost of that wind turbine, so in the entire cost, just you can say it's you have to spend almost 5 crore per megawatt. So the 20% of the cost will go to the rotor components. So just you can say this blade cost and this cost is almost 20%. And if you are taking that gearboxes, generator, and this controller and all, it will take 35%. So here 35% is a huge contribution to the gearboxes and generators. So that's what people are working to reduce the cost by eliminating this gearbox. So just we'll discuss in future slides how they can able to eliminate this gearbox in a wind turbines. And 15% of the cost will go to the tower and yaw mechanism. So this tower and this yaw mechanism can cost around 15%. I hope you can understand some basic components of the wind turbine. So if you have any doubt, you can ask me in between. So when we come into the turbine, it's very important to understand the basic characteristics of the wind turbine. So just we are having the rotor, and the rotor is connected with the low speed shaft. From the low speed shaft, just we are connecting to the generator through the gearbox. So just here, that rotor can convert the kinetic energy from the wind to mechanical energy, right? So that's mechanical, and I mean, you can calculate the mechanical power in the rotor is of rho AV cube Cp. So this is very important equation when you are working with the wind energy conversion system. So this is the power output from the turbine, and that's what just here the M means it's a mechanical power. So this mechanical power is the input to your generator. So just this is the output of your turbine and input to your generator, because just you are getting a mechanical power from the turbine, and that mechanical power you are transmitting to your generator. So here the input to your generator or output from the turbine, you can call it as mechanical output power. So that is of rho AV cube Cp. So here the rho is air density, then the air density is depending upon the location and the time. So this is not in our hand, it will keep on change. And A is area of the wind turbine. So the area of the wind turbine depending upon the length of the blade. So if you are increasing the length of the blade, then the area also will change. So if you are increasing the length of the blade, then area will increase. So what will happen if area increases? The power output from the turbine also will increase. So if your area increases, your power output from the turbine also will increase. So that's what. But here during the installation itself, the manufacturer can decide the length of the blade. So normally the length of the blade is 80% of the it's a maximum 80% of the tower height. So that is the maximum length of the blade. And another point here is another variable here is power coefficient. So this power coefficient is depending upon the bits limit. So just here, depending upon the aerodynamic properties of the wind turbine system, then just we are having the power coefficient Cp. So this Cp depending upon the bits limit. So here the bits value is, maximum value is 0.59. So here the bits limit is 0.59. So this bits limit will decide the conversion efficiency of the wind turbine. So here by having the bits limit of 0.59, so I can say the power conversion efficiency of the wind turbine is 59%. So my theoretical efficiency of the wind turbine is 59%. So that's the maximum efficiency. But in a real time, the efficiency may change to 52%. So, and another thing is the output power of the turbine is depending upon the wind velocity. So here V is the wind velocity. So I can say the output of the turbine is cube of the wind speed or cube of the wind velocity. So once you are changing the 1 meter per second wind velocity also, it will give a huge impact in the power output of the turbine, because it's a just we are having the cube of the your power output is cube of the wind velocity. So this is the power characteristics of your wind turbine. So here just we are having the power output of the turbine. So by varying the wind velocity in power output of the turbine, so just you can plot the curve between your turbine speed and output power of the turbine. So here, if you look at it, just you can consider the 0.5 per unit wind velocity. So if you are considering the 0.5 per unit wind velocity, just you can substitute the wind velocity in that equation. So you will get this curve for the different wind turbine speed. So for different wind turbine speed, just you are getting this curve. Then for just you can substitute 0.6 per unit, this one, and 0.7 per unit, this curve, and 0.8 per unit, you'll get this curve. Till 1 per unit, just if you're plotting the curve for the 1 per unit of wind velocity, you'll get this curve, right? So here, x-axis is the wind turbine speed, that means turbine speed, and y-axis is the output power. So now, for the sake of understanding this curve, what I can do is I'll consider the 0.9 per unit wind velocity. So at the particular time, but here just we have considered some steps in terms of 0.1 per unit. But in a practical condition, your wind velocity will keep on change. So just we'll get number of same type of curves. So for understanding purpose, just we have considered the 0.1 per unit steps. So just that's what we have plotted the power output of a particular wind velocity. So here for sake of study, I have considered the 0.9 per unit wind velocity. So at 0.9, I consider that at particular of time, I'm getting a 0.9 per unit wind velocity. So that my wind velocity is constant, but it's in real time, it's not constant. For the sake of study, I consider the constant wind speed. So at a constant wind speed, you are getting the power output curve as this one. This is the power output curve for 0.9 per unit. Okay. So at this, my wind velocity is 0.9 per unit. I can consider that my turbine is rotating at this speed of 1.2 per unit. So your wind velocity is 0.9 per unit. At that time, I'm rotating my turbine at 1.2 per unit of the turbine speed. So what's my output power? So my output power at this point is 0.5 per unit, right? So if I'm operating my turbine at 1.2 per unit at the time of 0.9 per unit wind velocity, my output power of the turbine is 0.5 per unit, right? 0.5 per unit, because this point is here, right? This point is here. So my output power is 0.5 per unit. Remember? Right. So I'll consider, so another, my wind velocity is this one, but I'm operating my machine at 0.6 per unit. So at 0.6 per unit also, my output power is 0.5 per unit, right? So here, just you are operating at this point, you can operate your turbine at any speed, right? So your turbine speed may locate here, locate here, locate here, right? At that time, my turbine output power is less as compared to this point, So if I'm operating my turbine, at 0.9 per unit, my output power will be 0.75 per unit, right? So at this point, at this particular point, if I'm operating my turbine at this speed, I'll get this point. So at this point, my power output from the turbine is maximum, right? So 0.75 per unit. So what I can conclude is, if my wind velocity is 0.9 per unit, I have to operate my wind turbine at 0.9 per unit of turbine speed. So then only I can able to get the 0.75 as a maximum power output from my turbine. So very clear. So if I say my wind velocity is this, then I have to operate my turbine at this speed, 0.9 per unit speed. Then only I'll get the maximum power from the turbine. So this is the one case of wind velocity, but wind velocity will keep on change. If it's a 1 per unit, I have to operate my turbine at 1 per unit speed. So then only I will get the maximum power from the turbine, right? So this is called maximum power points for each wind velocity. So here, for achieving this maximum power points in this different wind velocities, you have to adjust the speed of the turbine. So just you have to control the speed of the turbine. So for achieving the maximum power point. So it's very clear. If you want to implement the maximum power point tracking algorithms, so if you want to catch that point, you have to change the speed of the turbine depending upon the wind velocity. So this is the key reason behind the maximum power point tracking algorithms. So here, for achieving this point, you have to change the speed of the turbine. So how you are changing the speed of the turbine is up to you. So how you are controlling the speed of the turbine is up to you. Whether you can use any mechanical control to control the speed of the turbine, or you can use any electrical control, right? So that we will discuss in later without confusing in this slide. Here, so for each and every wind velocity, just we are having a one maximum power point. So just we can attach this all the points. So we'll get the nonlinear curve. So that's a curve here in the second diagram. If you look at this, just we are having the this nonlinear curve here. So only this region, from this region to this region, you have to implement the maximum power point tracking algorithms. So from cut-in speed to rated speed, right? So here, this is what just we are getting from the this curve. So that's what we can see here. From this point to this point, they will say it's a generator control. Why they are saying it's a generator control means, as an electrical engineer, it is easy for us to control the speed of the machine. So if you are controlling the speed of the machine, you can able to control the speed of the turbine, because the machine is coupled with the turbine. So once you are controlling the speed of the machine, you can able to control the speed of the turbine. So it's an indirect control. So you can say indirectly you are controlling the speed of the turbine by controlling the speed of the electrical machine, right? So here, after this rated, rated speed, whatever the wind velocity increases, your output from the turbine is constant. Your output from the turbine is constant. So that's what you can look at here. So after the rated wind speed, your output power from the turbine is constant. So here they will implement the pitch control. So pitch control means it's a mechanical control. By changing the tilt angle of the blade, you can able to change the speed of the turbine. So here, it's very simple. You can understand. In our ceiling fans also, our wings are not flat. Just you can see, look into it. It's tilted, right? So then only just you'll get the it will suck the air on the upper side and give the airflow in the bottom, right? So the same concept in a wind turbine also, your blades are not flat, it's tilted. So by changing the tilt angle, you are changing the pitch of the blades. So you can able to control the speed of the turbine. So that's what they will call as pitch control or stall control, right? Pitch control or stall control by adjusting the tilt angle of the blades. So how they can change the tilt angle of the blades means, in every wing, they are having the motor to change the angle of the blade, right? So here they will implement the pitch control in the after the rated wind velocity up to cutout speed. So here I want to convey three regions. One is cut-in speed. So cut-in speed is a speed where they can start the wind turbine to generate the power. So below cut-in speed, they won't allow the generator to rotate. The reason behind is the losses are more below cut-in speed. The losses itself enough to compensate the generated power. So there is no use to operate the machine below cut-in speed. So after cut-in speed, they will allow to operate the machine till rated speed. They will implement the maximum power point tracking algorithm. So for implementing the maximum power point tracking algorithm is this region from cut-in speed to rated speed. So that's what they by changing the because you will employ the power electronic converters. So by changing the firing angle of the converter, you can able to change the speed of the machine. So just we are doing the speed control here from this region to this region. So that's what is the maximum power point tracking. So after rated speed, your output from the turbine is constant till cutout speed. So the typical value of the cut-in speed is 3 to 5 meter per second, and rated speed it's a 15 meter per second, and cutout speed it's a 20 to 25 meter per second. So here after 20 to 25 meter per second, they will stall the turbine. The reason is, if you are allowing the turbine to rotate above cutout speed, it leads to damage the turbine systems. So because of the gusty wind speed. So at that time, by changing the tilt angle of the blades as well as the electrical control, you can able to stop the wind turbine to rotate during the gusty wind speed. Right. So this is the characteristics of the wind turbine. So once you understand these characteristics of the wind turbine, then it will be easy for you to understand the requirement of the power electronic converters in wind turbine systems. So now it will be clear why we are using a power electronic converters in wind turbine systems. Here, only for this region purpose. Why? Because here just we have to implement the maximum power point tracking. So how we can implement the maximum power point tracking means by controlling the speed of the machine. So for controlling the speed of the machine, you need a power electronic converter. So that's called say electric. I mean, this wind turbine also kind of electrical drive. So that speed you can adjust from cut-in to rated speed. So that's what you need a power converter for wind turbine application. So now you can get to know the why the power electronic converters is required. So without power electronic converters, it's not possible to implement the maximum power point tracking algorithm. So any question after this? So I'll be happy to clarify any doubt if you have any. Yeah. So we move forward. Okay, when we come into the wind energy conversion system, we can classify the wind energy conversion system as grid connected systems and standalone systems. So here we are classifying the wind energy conversion system depending upon the, the output of the turbine. Excuse me. So in a grid connected system, so you are generating the power and you are injecting that power into the grid, right? So here in a standalone system, just we are supplying the local loads. You can say the local loads may be in a few kilowatt or in megawatts. So if you are assuming that I can able to supply the power, power to the house or power to the community areas or commercial buildings. So that and all, wherever you are not getting the electrical grid over there, you can prefer the standalone system, right? So here, when as an electrical engineer, just we have to look into the control variables. So what are the control variables in this both the systems? So when we consider the grid connected system, the control parameters in grid connected system is active power and reactive power. So in whatever paper you can take in research paper, if they discuss about the grid connected system, they will discuss about the active and reactive power control. So these two are the quantities to control grid connected system. In standalone system, so as a consumer, I'm not having any electrical grid. So if I'm connecting to some power supply, what's my expectation? My expectation from the power supply is constant voltage and constant frequency. So in a standalone system, you have to ensure that constant voltage and constant frequency to the loads. So here the voltage and frequency are the control parameters, right? Voltage and frequency are the control parameters in standalone system. In grid connected system, active and reactive power is the control parameters. So here you can take any paper. When we talk about the grid connected system, they will talk about active and reactive power control. In standalone system, voltage regulation and frequency regulation. In terms of AC microgrid, if you are having the DC microgrid, for standalone system, it will be very easy. Just you have to do only the voltage regulation, the magnitude, voltage magnitude regulation. Because in DC, just you have to maintain the constant voltage. Clear? So if you're looking at the grid connected system, in a grid connected system, in a research point of view, just I will classify it. Whatever the grid connected wind energy conversion system or grid connected photovoltaic system, they will touch upon some 3-4 aspects. So if you are taking any grid connected system paper in photovoltaic and wind energy conversion system, mainly they may talk about the active and reactive power control, that too independent control of active and reactive power control. And another aspect is they may discuss about the grid synchronization. So some people, they may work on the phase lock loops. So these phase lock loops will be useful for a grid tied inverter synchronization. Then in some people, they may work on maximum power point tracking algorithm, for implementation of maximum power point tracking algorithm in grid connected system. So another few people, they may work on the same way, same control system to compliance with the grid codes. So power system people, they may look into this aspect when they are talk about the grid connected system. And another small group of people, they may work on the islanding operations. So if your grid connected photovoltaic or grid connected wind energy conversion system is islanded, how we can supply to the loads. So in that aspect, they will work on the grid connected wind or photovoltaic systems. When we come into the standalone system, main thing is voltage and frequency regulation. And we can say it's a power balance. So here, when we are saying that we are supplying the power from the wind or photovoltaic, it's an intermittent one. Even the load also, it's an intermittent one. So it's not that much easy to match the supply and demand. So for that, people may work on the energy storage systems in standalone cases. So these are the aspects when we start to work on the wind energy conversion system and photovoltaic systems. So here, this slide will give the main components of wind energy conversion system. So earlier, just we have seen the components of horizontal axis wind turbine. Here, when we consider as a wind energy conversion system, these are the main components. One is in a mechanical side and another one is in an electrical perspective. So in a mechanical parts, just you can say it's a rotor. So rotor is a hub connected with the blades. So this rotor can convert the kinetic energy from the wind to mechanical power, right? So that's what you are saying, that the rotor is used for power conversion. So because it's you are converting the kinetic energy from the wind to mechanical energy. So just we are saying that it's a power conversion. Why I put control here means earlier when we talk about the characteristics of the wind turbine, just we talk about the pitch control. So how you are implementing the pitch control means by changing the tilt angle of the blades. So just by changing the tilt angle of the blades, you can able to control the speed of the wind turbine. So that's what they put the control also here, because we can able to control the speed of the turbine by changing the tilt angle of the blade. So that's what the rotor can be used for power conversion and control. So here at this point, you will get the mechanical power. So this mechanical power is transmitted to the generator through the gearboxes. So why we have used the gearboxes means to match up the speed of the wind turbine rotor and the generator, because the rotor speed is 50 to 100 RPM. Here the generator speed is 1500 RPM. So you have to match the speed of the turbine as well as generators. So for that purpose, you are using the gearboxes. So that's what you are saying, that the gearboxes can be used for power transmission. So here again they put gearbox is optional one. Why they have mentioned the optional one means nowadays people are working for gearless wind turbines, because the 30% of the cost, the gearbox the gearbox cost is higher. So that's what people are working to eliminate the gearbox. So that's what they put the gearbox as optional. So normally in the once you are eliminating the gearbox, what will happen? The rotor speed is in 50 rpm to 100 rpm. Then you have to match with the generator. So you have to work on the generator to generate the power at the low speed. So nowadays people are working with permanent magnet synchronous generators. The reason is in the low speed itself, it can able to generate the power. So for that gearless wind turbines, people are working with permanent magnet synchronous machines. So this generator, so it will convert the mechanical power into electrical power. So that's what just we are saying. It's a power conversion and control. And here again, we are using the power converters. These power converters are used to control the speed of the turbine to implement the maximum power point tracking algorithms. So here, earlier cases, they have come up with the fixed speed wind turbines. In a fixed, if you don't want to implement the maximum power point tracking, you need not to use these power converters, right? So that's what again they put the optional. In earlier 1990s, they have the fixed speed wind turbines. So in a fixed speed wind turbine, there is no maximum power point tracking algorithms. So that's what they haven't used the power converters. So that's what they put the power converters as optional here. Then the power transformers. Then what's the purpose of power transformers here means? Just you have to match up the grid voltage and your wind turbine voltage. Maybe I can say in the primary distribution network, the voltage is 11 kV. My wind turbine power output is in 440 volts. Then just you have to match the 440 volt and with the 11 kV of grid. So for that purpose, they may use the power transformers in between it. Not only for match up the voltage, the power transformer will give the great isolation of the grid and the wind turbine. So what's the purpose of isolation? This electrical isolation. So whatever, if any fault happen in the grid, that won't affect your wind turbine. Or if you are saying if you are having any fault with wind turbine, that won't affect the grid. So it will provide the great isolation between grid and your wind turbine. So that's the purpose of using the power transformer here. So these are the main components in the wind energy conversion system. So the power converters nowadays in the modern wind turbines, the power converters are playing the major role. So that's what what are the wind turbine, variable speed wind turbines are coming nowadays that are come up with the power converters and controllers. So when we come into the wind turbine concept, earlier I said about the fixed speed wind turbine, right? The fixed speed wind turbine, there is no power electronic converter employed in this fixed speed wind turbines. And just we are having the gearboxes because they will connect directly the rotor to the generator, and the generator type is screw cage induction generators. So why they have used the screw cage induction generator means here, if you are giving the power supply to our normal induction motor, it will, if you're connecting to the supply, it will act as a motor. Then in the same direction of the speed, if you are rotating your shaft above synchronous speed, the screw gauge induction motors will act as a generator. So if you are increasing the speed of the motor above synchronous speed, then automatically it will convert from motoring operation to generation operation. So only your current direction will change in the at the stator terminals. So that's what it's they say it's a fixed speed wind turbine. Here they said it's a fixed speed wind turbine. It's not an exact constant speed. It may operate in the speed variation of slip. So for higher capacity induction machines, the slip range is 3 to 5%. So the machine can operate at 3 to 5% slip range. So 3 to 5% slip range means, for example, if we consider our 4-pole induction motor, 4-pole induction machine, by considering the 50 hertz power supply system, the synchronous speed is 1500 rpm. So if you're operating the induction motor at no load, it may operate at 1480 rpm. If you are loading the machine, then it will go up to 1450 rpm. Depending upon, I mean, if you are having a small machine, the slip may be 10%. But for higher capacity, I mean, if you are going with 100 kilowatt, 200 kilowatt, the slip range of the induction machine is 2 to 5%. So that 2 to 5% is possible with this fixed speed wind turbines. So here you are not having any power electronic converter in the fixed speed wind turbine. So you cannot able to implement the maximum power point tracking. So with the absence of maximum power point tracking, your energy output from the turbine also less as compared to the variable speed wind turbines. So in earlier days, till even nowadays also, just we are having this fixed speed wind turbines. But whatever the turbine they have installed, it's a fixed speed wind turbines. So after 2005, even early 2000s, they have come up with some variable speed wind turbines. But nowadays, whatever the wind turbines they are installing, just they have come up with the variable speed wind turbines, so that they can able to incorporate the maximum power point tracking algorithm. So by incorporating the maximum power point tracking algorithm, the energy captured by the turbine for a year is more than the fixed speed wind turbines. So almost the energy captured by the variable speed wind turbine is more than 30% compared to fixed speed wind turbines. So that's what they prefer, the variable speed wind turbines for wind energy conversion systems. So in this case, the gearbox stage is also it's less as compared to fixed speed wind turbine, because just you are having the power electronic converters, so that you can able to control the speed of the machine, so that you need not to use a more number of stages in the gearboxes. These are the generators normally employed in the variable speed wind turbines: permanent magnet synchronous generators, W-fed induction generators, and WRIG machines. So here, permanent magnet machine and this TFIG and WRIG, normally they will use the slip ring induction machines. Just you have studied in your electrical machines, there are two types of induction machines. One is spool cage machine and a slip ring machine. So these two topologies, DFIG and WRIG, they are employing the slip ring machines as a generator. First, we'll discuss about the fixed speed generators. In a fixed speed generators, there are two types. One is synchronous generator and spool cage induction generator. Normally, they won't prefer synchronous generators for wind turbine application. The reason is, if you for a synchronous machine, if you want to get a constant frequency, then you have to operate at a constant speed. So I can say 4-pole machine 50 hertz if you record, then you have to always operate at 1500 rpm. Even if you're operating at 1502 or 505, the frequency will change, right? So that is not permissible in the wind turbines. So wind turbines, the speed will keep on change. So that's what they won't prefer the synchronous generators for wind turbine application. Another reason is, in a synchronous machine, just you are having the field and armature. So for field, you have to give a DC supply. So here you need a separate DC supply for synchronous machine. So normally wind turbines are located in the rural areas. So for maintaining the DC as well as AC in the on the turbine, it's a tedious job. So that's what they won't prefer the synchronous generators for wind turbine application. So the best candidate is spool cage induction generators. So why they have used the spool cage induction machines for wind turbine application is because of the rugged construction. So you need not to require the much maintenance for this spool cage induction machines. So that's what they prefer, this spool cage induction machines for wind turbine application, as well as synchronization not required. Even in our lab, just we have fought with the synchronous machine to connect to the grid. So even just we have used some Doppler methods or synchronous for connecting to the grid. But in terms of spool cage induction generators, it's directly connected to the supply. So it will act as a motor. Once you start above the synchronous speed, it will act as a generator. So here you need not to factor any kind of synchronization. So that's another major advantage with the spool cage machines. And here it required two supply system, but here only single phase because the rotor is made up with copper bars and welded at the end of the rotor and will be short circuited. So here only the accessible windings are stator windings. So it's a single phase machine. And even if we are having this kind of advantages with this spool cage induction machines, the major disadvantage is lagging power factor operation. So why I'm saying it's a lagging power factor operation in the spool cage induction generator as a disadvantage means, here whenever it will operate as a motor or generator, it always takes the reactive power from the grid. So if you are taking the reactive power from the grid always, then just there is some power quality issues in the grid side. So that is not advisable one. So here, for that purpose, for in reducing the reactive power drawn from the grid, people may use the capacitor banks at this point. So if you are using the capacitor bank, this capacitor banks will provide the reactive power support to the machine. So why it's taking always reactive power means the machine required the magnetizing current. So for that purpose, it always take the reactive power from the grid. So for that purpose, you can use the capacitor banks. So by using this capacitor bank also is another disadvantage. Why? Because selecting the capacitor values. So just you can say this machine can operate from low power to or low rate. You can say 10% load to 100% load, full load condition. So during the low load condition, the capacitor bank is you need a capacitor bank with a less number of capacitor values. If you are going with full load condition, the capacitor bank values would be higher. But here you connected the fixed capacitor bank. So what will happen if you consider the full load condition? The capacitor bank is higher, so we can connect the high value of the capacitor. Once the wind is less, then it will operate at the low power. You can say the low load condition. So during the low load condition, what will happen? So this capacitor can provide the reactive power support. Then the higher value give the higher value of the magnetism current to the grid. So just we are injecting the reactive power to the grid. So it leads to the leading power factor operation. So that is not advisable in terms of power quality point of view. So that will give some kind of problem. So that's what people nowadays, they are working on the switched capacitor banks or StatComs and all in this point. So that also you can take it as a research problem and work on it. So another thing is self-excited induction generators. So in self-excited induction generators, normally used for supplying the standalone loads. So earlier case, we have talked about the fixed speed wind turbines. So that can supply your loads. So here, supply your grid. Here, just if you are having the loads, so how we can use the spool cage machine for supplying the standalone loads. So as I already mentioned, if you want to make the spool cage induction machine as a generator, then just you have to operate that generator above synchronous speed, right? So above synchronous speed. So even if you operate above synchronous speed, also you will not get any voltage in the static terminals. Why? Because just you are not having any magnetism, because the loads are RL. So these RL loads will not provide any magnetizing current to the machine. So this will not generate the power. So for that purpose, you need to connect the capacitor banks. So these capacitor banks will provide the magnetizing current to the machine. So it will build up the voltage at the static terminals to supply the loads. So here in a machine, just we are having the residual voltage. So with the help of residual voltage, with the help of the capacitor, the voltage will build up in the static terminals, and you can connect to your load. So again, loads also, it's not in your hand. If I consider my home, sometimes I may switch on and switch off the lights and fans, even just I'm having the 5 rooms. So even the depending upon the person, the load also can change. I may like the fan, and my brother or my parents won't like the fan or air conditioner, they will switch off. So it's not unique load, right? So load will keep on changing. Sometimes I may feel, okay, I need to switch on the AC. I switch on the AC. So here the loads also, it's a variable one. And here when we consider the input, the wind also, it's a variable one. So it's not easy to match the demand and source. So demand also in a different pattern, and source also have a different pattern. So here you cannot able to match the supply and demand. So always you will get the problem of voltage and frequency regulations. So for this purpose, you cannot use this kind of wind turbines for supplying the frequency sensitive loads. You can use the frequency insensitive loads, so like heating loads, so that can able to supply here, but we cannot use the frequency sensitive loads for this case, right? So we can say the voltage and frequency of this terminals are depending upon the speed of the wind turbine, the capacitor value, again the load parameter. Load is also keep on change, and generator parameters. So that's what just we can develop some kind of power converter topologies for providing the constant voltage and constant frequency to your loads, as well as for matching the power. Just we have to incorporate some kind of energy storage systems. So when we move to the variable speed generators, there are 4 types of variable speed generators. The first 2 types on the top of your slide, one is a permanent magnet synchronous generator and spool cage induction generator. So permanent magnet synchronous generators are connected with the back-to-back converters to the grid. Here, just we are having the spool cage induction generator is connected to the grid through the back-to-back PWM converters, right? So here, what I want to convey from these 2 topologies are, if you say the power converter ratings, this power converter rating should be equal to the machine rating. So if I say 5 megawatt of the turbine, so for 5 megawatt of the turbine, I can use 5 MVA rating of the generator. So this power converter rating, you are having 2 converters. So this converter rating also should be 5 MVA, because whatever the power is generated in the generator, that can be channeled through this PWM converters, right? So your converter rating will be equal to the machine rating. So that's what I'm saying is a full rated power electronic converter. So the converter ratings are equal to the machine rating. So in this case also, the converter ratings are also equal to the machine rating, right? So here with these generators, it's possible to control the active and reactive power control, because here this converter can be used to maintain the voltage at the DC capacitors, and this PWM converter can take care of the speed control of the turbine to implement the maximum power point tracking. So here the reactive power, the power factor operation at the point of common coupling will be taken care of the grid side inverter and maintaining the constant voltage at the DC capacitor. Then this converter can take care of the control of the machine. So with this is synchronization problem. So for synchronization problem, just we have to implement the phase lock loops, right? So normally for grid side inverters, they will work on the phase lock loops. Okay, so next when we come into here, in a permanent magnet is there in the flip. So that's what whatever the speed can able to generate the power at variable voltage and variable frequency. So in this case, what will happen, as already we have discussed about the spool cage induction generators. For spool cage induction, if you want to operate the spool cage induction machine as a generator, you need a reactive power. So this reactive power can be supplied by this because these back-to-back converters are bidirectional converters. So this converter will supply the reactive power support to the machine, so that you can say you can able to control by controlling the firing angle of that converter. You can able to change the speed of the turbine. So for MPPT operation, they will use MPPT, and reactive power support, they will use the machine side converter. And again, for grid side control, just they will use the grid side inverter for unity power factor operation, as well as for maintaining the constant voltage at the point of DC link and all. This converter control can be taken care of it, right? So here also synchronization problem. So they will use the phase lock loops for grid synchronization. So these are the two types, and bottom of it, another two types you are having. So wound rotor induction generator and doubly fed induction generator. So in this wound rotor induction generator and doubly fed induction generator, they will use the slip ring machines. So this machine also slip ring machine. This machine also is a slip ring machine. So depending upon the power converter topology, just we are named as a doubly fed induction generator. Here we say it's a wound rotor induction generators, right? So here the major advantage of these two topologies are the converter rating. So whatever the converter rating you are using here is a 30% of your machine rating. So here just we are using the full power converter rating equivalent to the machine rating. But in the bottom of these two topologies, whatever the converter topologies you are employing, these are 30% power rating. The reason is in a slip ring machine, in a rotor, you will get the slip power. So slip power, I already told you, in a induction asynchronous machines, the slip range will be maximum. You can say 3 to 5%, right? So if you are saying if for a higher rating machine, it's a 2 to 3%. So only that the slip power can be recovered here. So only the slip power is recovered. So that's what the machine rate, the converter ratings are only less as compared to the top two topologies, right? And here now just we'll discuss about the wound rotor induction generators. In wound rotor induction generators, just we are using the diode bridge rectifier and chopper at the rotor terminals. So by varying the duty ratio of the chopper, because in a chopper just we are having only one switch. So by controlling the one switch is very easy as compared to all the topologies, because here in the top two, if you look at it, how many switches you are having? Just we are having the 12 switches. So each converter having the 6 switches. So totally 12 switches are there. So we have to control all 12 switches. But in this topology, just we are having only one switch, only one control switch. So that's very easy to control. So by varying the duty ratio of the chopper, you can able to vary the rotor resistance, rotor equivalent resistance. So once you are changing the rotor equivalent resistance, you can able to control the speed of the generator. You can able to control the speed of the generator. So by controlling the rotor resistance value, rotor equivalent resistance value, you are controlling the speed of the generator. So here only one switch at the same time. The control is very easy. And here, if you look at it, in all these three cases, the power converter is connected to the grid. So in this case, there is no power electronic converters directly connected to the grid. It's only connected to the rotor terminals. So the big advantage is, even if you are having the one single switch, if you are connecting to the grid, it obviously inject the harmonics to the grid. So here there is no converter connected to the grid, so you can able to reduce the THD values in this case, because just here even this machine itself will give the isolation, as well as just you are having the inductance, so that will give the filtering effect to your this converter harmonics injections. So when we come into the doubly fed induction generators, here in doubly fed induction generators, they will use a reduced size of converters, only 30% power converter rating. So because of the only just you are dealing with the slip power, right? So here the major advantage of W-fed induction generator as compared to wound rotor induction generator is you can able to increase the wide speed range. But here the speed range is above. I mean, this topology will work as a generator above synchronous speed, right? So above synchronous speed means for 4-pole 50 Hz system, I can say 1500 is synchronous speed. So it will operate as a generator from 1500 to 1520 RPM. But in this case, just we can able to operate this machine as a generator below synchronous speed also. So below synchronous speed means you can say below the you can say 1500. So 20 RPM I can take it as a range. So 200 or yeah, you can take it to 20. So 1480 also I can operate as a generator. 1520 also I can operate as a generator. So just we are having the 40 RPM range, but here in the wound rotor induction generator, just we are having 20 RPM range. Just for sake of explanation, I have taken the 20 RPM. So here we can say just we are having the wide speed range because of the subsynchronous speed of operation. So just we are having subsynchronous speed as well as supersynchronous speed range. So it is possible to operate in the wide speed range. So what is the advantage by having the wide speed range? It will be very easy for us to implement the maximum power point tracking algorithm. So that's what it's a beauty of the W-fed induction generators. So do you have any questions up to this slide? If you're having any questions, I'll be happy to answer.
Hello, sir.
Sir?
So Vijay sir, at the end of the session, we'll share a PDF or a file with the questions which are asked in YouTube, sir.
Okay, sir. Okay.
At the end of the session,
they are not. Now they are not in.
Yeah, they are in YouTube streaming only, sir.
Okay, yes, sir. Okay, sure. Okay, I will continue it then.
Yes, sir. Another 15 minutes there.
Yeah, sure.
Okay, thank you.
So another, with the help of the literature survey, just we have proposed some grid-connected WRIG system. So in this case, just we have proposed some novelty in this topology. So earlier, when we look into the literature survey, they haven't used any kind of variable resistors in a rotor terminal. So just if you look at that literature, all researchers, they have considered as a fixed resistance. By having the fixed resistance, just by varying the duty ratio of this switch, then they have changed the resistance value at the rotor terminals. So that's what they have controlled they have implemented the maximum power point tracking by controlling the speed of the turbine. So earlier case, they have done this one. So what we have proposed is, earlier case, they have used the fixed resistance. So all the slip power is wasted in the resistance itself. So what we have proposed is, instead of wasting the energy in the fixed resistance, just we can use it for space heating applications. Or for, normally wind turbines are located in the remote areas. So the, you can think of it because here, they may use 1 megawatt of the turbine. So 30% means it's almost 200, 300 kilowatt. So 200 to 300 kilowatt of the power is wasted in the resistors. So instead of wasting the power as a heat in the fixed resistors, we are proposing that you can use it for space heating application, as well as you can use it for drying up the crops and all, because it's located in the remote areas. So the rural people also can get benefit out of it. So that's what just we have considered as a variable risk. Because if you are giving the, if you are supplying the load, then again it's a load, so variable load. So that's what we have considered as a variable resistance here. At the same time, so people ask that even if the local people may not have that much demand, so what you will do the excess energy? So for that, we have incorporated the battery here. So again, people ask that if you're going with battery storage, then you need to concentrate on the charging control, chargers and all, right? So for that purpose, what we have proposed is we have taken the simple fast recovery diode. By connecting the fast recovery diode at this point, you can able to charge the battery whenever the power is excess. So whenever the power is demand is more, then your battery will not get discharged, because you can consider that whenever the load is not available, there is, I mean, during a low load condition, what will happen during a low load condition? So here the voltage will be higher, because during low load condition the resistance value is higher, so just you will get the higher voltage here. So this voltage will be higher than this battery voltage. So that time what will happen, this diode get forward bias, and the excess power is used to charge the battery. So another condition is, when the load is more, what will happen? It's a short circuit. So once it's short circuit, here the voltage is zero, during 0 or less than this voltage. So this will be reverse bias, so your battery will not get discharged. So here, that's what we have proposed with this system here. Even if you propose some system, it's not always it's 100% a good system. Even you are having some limitation with that. So here with our system, the limitation is, if your battery is fully charged, you cannot discharge the battery. So there is a missing of BMS system. For that case, just you have to swap the battery. So that we have to do manually. So once the battery is charged fully, then you have to replace the battery with uncharged one. So that I can do it manually. So that's a limitation with this system. So even in the control strategy, just we have proposed both MPPT as well as constant output for mode block. So here for MPPT operation, just we have implemented the speed sensorless algorithm. So here just we have estimated the speed with the help of stator voltage and rotor current. Again, the stator voltage, it's just the frequency, and from the rotor voltage you can able to get the slip frequency. So once you know the slip frequency and the stator frequency, supply frequency, then that will be easy for you to estimate the speed by using the relation between the slip and synchronous speed, right? So that's what we have done here. Just easily can able to implement, you can estimate the speed. So with that, by looking at, by measuring the wind velocity, we can able to get the optimum speed for that particular wind velocity. So that optimum speed you are getting here, an actual speed is known. So you can compare it and you can give it to the PI controller. So here we have used the descent mode block, because we have used the two modes of operation as a constant output power mode. Constant output power mode means whenever your demand is coming from the grid, so that demand has to be satisfied by your wind turbine. So for that case, just we have given the desired power from the grid, then that can be compared with the calculated power. Then P error is generated. If the demand is there, then it will operate in the constant power output mode. When the demand is not available from the grid, then it will operate in the MPPT mode block. So here is, as usual, just we are having the PWM controller block. So this is the hardware setup of our work. So just we are fabricated single condition circuit and inverters, even the DSP controller board, we have get it from the ISC Bangalore. So this is our work. So due to the time constraint, I'm not going to discuss about the WF induction generators. So with that, with this topic, I'm going to complete it. So if you're having any questions, please send it to the coordinator. So I'll be happy to answer for that questions. Thank you.
Hello, sir. Thank you very much, sir. Now, yes, I'll share the questions posted in the YouTube, sir. Let me.
YouTube. So
Yes,
I have to
let me
go to
post.
YouTube.
No, sir,
YouTube.
no, sir. I'll just present it here itself. I'll present it here. 1 minute. Sir.
Hmm.
So is it visible, sir? I just shared the screen.
Yeah, sure, sir, sure. I'll go to. Yeah. What is isolated system? So I already mentioned that isolated system means you're not connecting your generator to the grid. So just you are supplying your local load. So just for example, I'm having the home. So my home is not connected to the grid. So just I need a power supply for my loads. So for that purpose, just I'm supplying my home alone by using the wind turbine or photovoltaic system. So in that case, just I have to maintain the constant voltage and constant frequency from my power supply. So just the constant voltage and constant frequency, you have to maintain it, as well as just you have to maintain the power balance. So for that purpose, because load is intermittent one, and your your source also it's an intermittent one. So for matching the supply and demand, you need to use battery energy storage system. So once you are having the battery energy storage system, so the power balance will happen, so that we can able to maintain the constant voltage and constant frequency at the loads. That's the first question. Then another question is, what is principle of gearbox to max speed generator? Yeah, I already told you. Just we are having the gearbox ratio. So your turbine speed is some 50 to 100 RPM. Then your generator speed is 1500 RPM. So even if you are reducing the number of poles, it may come down to 1000 or 1200 RPM. So how you match the 1200 RPM generated with the 50 to 100 RPM turbine? So for that, you need to use the gearboxes. So the gearboxes, depending upon the speed difference, just you have to go with the number of stages in the gearbox. So another person asked, can pitch angle be less than 0 degree? Please relate it if possible with any real scenario and how this angle is decided. Yeah, pitch angle cannot be 0 degree. If you say the pitch angle is 0 degree, then in aerodynamic efficiency will be less. So we cannot able to harvest the energy from the wind. From the wind. So because the blades are flat, so you cannot, your blades won't rotate it, right? So because of that tilt angle, the pitch angle, your blade, you're rotating your turbine, right? That's the aerodynamic principle. So here you cannot make 0 degree. At the same time, for controlling the speed, I suppose during the gusty wind speed, I have to stop my wind turbine, then you can make it 0, right? During that, that act as a brake. Next question is, if you can focus a little bit on the feasibility of permanent magnet index. So that is, here I want to clarify, say that there is no permanent magnet induction generator. So it's a permanent magnet synchronous generator. So here, permanent magnet synchronous generator can be used for low power application as well as in megawatt range. So even the gearless wind turbines also, they will prefer the permanent magnet machines. The reason being is the permanent magnet machines can able to generate the power during low speed also. So that's what you can directly connect your generator to the wind turbine without any gearboxes. So for even your small turbines, even in your buildings, in some buildings you may find that some small wind turbines, so 5 kilowatt or 10 kilowatt. So in that also they won't use the gearboxes. So for that purpose, just we can use the permanent magnet synchronous machine, not a permanent magnet induction. There is no permanent magnet induction generator. So another question is, explain the concept of inertia control, how it will be employed. Yeah, it is implying the system, ma'am. But the inertia control, normally it's a mechanical control. So in a mechanical control, the response is very, if you're going with large wind turbines, the inertia is more. So the response of the control system is less. So that's what normally they won't prefer the inertia control for implementing the maximum power point tracking. The inertia control normally they will use to stall the wind turbine, or for during that rated speed to cutout speed, they will implement this inertia control. Why do turbine gearbox fails? Yeah, gearbox fails means it's because of friction, or because of even the cost of the wind turbine is higher. So that's what they are trying to eliminate the gearbox from the system. At the same time, the gearbox cost is higher. So to reduce the cost of the system, they are going with the gearless wind turbine. Otherwise, gearbox's efficiency in all, it's good. It's a 98%. So we can go with the gearboxes, but the cost of the system will go high. So for reducing the cost of the system, people are working on the gearless wind turbines. Another question is, DFIG can be used in any speed as per your presentation. So there is no need governor for this type of generator. It's not required. So there is no need of governor, because here there is no concept of governor for this generators. The reason being is wind is will keep on change. So we cannot able to control the speed of the wind turbine. By nature, your wind velocity is changing. So for controlling the speed of the wind turbine, you can go with the generator control. So generator control or pitch control. So that's enough. So DFIG, why I'm saying is it's not for any speed. I'm saying it's a subsynchronous speed and supersynchronous. 30% below, 30% above. So that's what you are getting the wide speed range. There are 4 wind turbine models. Which one is the most suitable for wind energy? When we are looking at the wind turbine topologies, depending upon the size and depending upon the location. So if I say it's a megawatt turbines, permanent magnet synchronous generator and doubly fed induction generators are preferred candidate. So for large size of wind turbines. For small scale turbines, if you are going with 5 kilowatt, 10 kilowatt, then permanent magnet synchronous generators are best suitable candidate. And if you are earlier wind turbines, if you look at the 100 kilowatt, 200 kilowatt, if you don't want to use any power electronic converters and all means, then spool cage induction machines are best candidate. So it's depending upon the location and depending upon the size of the wind turbine. So whether it's a fixed speed or variable speed, if you are going with the variable speed wind turbine, the power electronic converters will be there. So for that case, just you can use for higher wind, higher capacity machines, you can prefer the EMSG and DFIG. For small scale wind turbines, I can say 5 kilowatt, 10 kilowatt, or 15 kilowatt, then your permanent magnet synchronous generators are best candidate. Can we use voltage source converter for reactive power management? Yeah, whatever the converters, PWM rectifiers I mentioned over there, that and all, it's a voltage source converters. So that voltage source converter only, it will give the reactive power required by the spool cage machines, as well as reactive power support to the grid. Those are voltage source converters itself. Then another person asked, sir, permanent magnet synchronous generator is tested and already commercialized. Yeah, it's commercialized. I'm talking about the permanent magnet induction generators, as it has shown some advantage over the SEIG. Here, the operation is totally different. That's what. Here, you have to understand what is synchronous machine and asynchronous machine. So induction machines are asynchronous machines. If you talk about the permanent magnet, is a permanent magnet machines. You can say PMSM or BLDC, that and all comes under the synchronous machines. So here you cannot, for reactive, why the permanent magnet synchronous generators are had advantage means it doesn't require any reactive power support from the grid. So for that purpose only, just we are using the capacitor banks to supply the reactive power. So that's what just I want to mention here. sorry, sir. Research is going on in this direction. Some people come up with the IEEE transaction. I don't know whether they have come up with the school cage index. I mean, permanent magnets inductance generator. They are doing with the permanent magnet synchronous meshing. Even they are working with the reluctance meshings. So the I mean, they're even Professor Beam Singh from IIT Delhi. He is working on reluctance meshings, but they are not coming with the permanent magnet induction generators. Just and here a new tone. So anyhow, I'll check into it. So they are working on reluctance meshings. Maybe they may change the name as a permanent magnet induction generator. I don't know.
Okay, sir. I think that's all the questions in YouTube, sir.
Yeah, sure, sir, sure.
Thank you very much, sir.
So thank you, sir. Thanks for the invitation. I hope participants are enjoying my lesson session.
Yes, sir.
Yes, sure.
Sir, we have discussed on the basics of renewable energy, then recent advancements in them. Then sir has explained the basic concept of wind energy conversion system, what is pitch control, what is yaw control, what's the need of power converters in wind turbine. Then there is some other discussion on fixed as well as variable speed wind turbine. And sir has discussed the various topologies of converters used in wind turbines. So this is one area where lots of research are going on. So I hope this presentation will help the people working in this area to go further into their research. So thank you very much, sir. Thank you for accepting our invitation and spending your valuable time with us. Thank you very much, sir.
Thank you, sir.
Okay, sir. Thank you.
So shall I move?
Yes, sir. Yes, sir. Thank you,
Yes,
sir.
sure.
So the feedback forms are shared in YouTube. Okay, so just upload them within the next 15 minutes. So the next section will start sharply by Very good morning to all. So now we'll go on to the next session, parallel operation of power electronic converters in a DC microgrid. So let me introduce the guest speaker, Dr. Amitesh sir from NIT Silchar. Dr. Amitesh Kumar was born in Bihar, India in 1986. He has received his BTech in Electrical and Electronics Engineering from Shastra University, Tamil Nadu. He has done his MTech in Powertronics and Drives from BITS Pilani in 2011 and PhD from Delhi Technological University from Delhi College of Engineering, Delhi in 2017. In June 2018, joined as Department of Electrical Engineering, NIT Silchar, India as Assistant Professor. He has been a recipient of WellTech Merit Scholarship for Excellence in Academics at BITS Pilani in 2011. He has been awarded under Commendable Research category at DT University for the year 2017-18 for publications in IEEE transactions. He has been also awarded prestigious POSOCO Power System Award under doctoral category. Dr. Amitesh Kumar has also co-authored more than 16 papers in leading journals and conferences, including IEEE transactions, IET journals, and others. He is an active reviewer in many leading journals line for IEEE transaction on industrial electronics, informatics, and industry applications. His research interests include analysis and design of power converters and its application in renewable energy sources, multi-level systems, power quality issues, AC-DC microgrid, and hybrid electric vehicles. He is currently heading 3 sponsored projects, one self-sponsored project on DC microgrid, other one SERV and MHRD project on electric vehicle, then DST sponsored project on sustainable DC community energy solutions. So it's a privilege to have you with us, sir. So I request Dr. Amitesh sir to take over the session.
Thank you, Sujit sir and Dr. Swapna madam. Okay, so I am audible to all. Okay, fine. So very good morning to all viewers. Okay, so we'll start our presentation with very brief about what is the necessity of this DC microgrid. Okay, so starting with introduction part, microgrids are the main building blocks of the smart grids, which are small-scale power systems that facilitate the effective integration of distributed generators such as photovoltaic, battery, and etc. Like most of the renewable sources that we see nowadays, like photovoltaic, battery, these are all like producing power that is DC in nature. So its integration with the DC grid is quite easy as compared to our conventional transmission lines that are AC in nature. Suppose if you want to charge the battery, ultimately the requirement is of the DC only. Suppose whatever appliances nowadays we are using for like laptop, mobile, or any electronic items that we see nowadays, mostly they are requiring the energy that is DC in nature. So if we are taking the power from the AC grid, so we require to have converters, like first AC to DC, thereafter again you need to step up or step down. So there are going to be number of cascaded converters that you have to use, and as you increase the number of converters, obviously each converter is going to have some efficiency. Okay, so suppose if I'm taking 0.9 also, there is going to be losses that is happening in the conversion process. So if we're using this DC microgrid, the losses that we can have with the multiple conversion that can be minimized. That is a major benefit with the DC microgrid. Another important thing is going to reduce our transmission losses. Like suppose if you are using the microgrid for local generation and local consumption, then it doesn't require actually taking out power from a very long line, so we can avoid the transmission losses substantially. It will saves our our bucks you can save, and emission, that is because generally whatever microgrid we are talking, we are like giving stress on integration of distributed generators. So basically those generators we focus mostly on sustainable energy, basically at using photovoltaic, wind. Okay, so that's going to cut our emission because of conventional conventional generation because of coal and thermal power stations. So microgrids can be operated in grid connected mode and islanded mode. depending on the location. Okay, it might be connected with the grid, and it may operate in the islanded mode also, and sometimes we say it's off grid mode also. Okay, so basically islanded and off grid, there are two different things. Islanded means that there is possibility being connected with the grid, but if I'm saying it's off grid, it means that system is completely isolated from the grid and it is going to be operated in a sustained manner without the help of any grid. The purpose of DC microgrid is basically your increase the introduction of your distributed PV units, reduce the energy dissipation, supply power to load via regular distribution line even during blackout of commercial grid. Like suppose if you if you're having a DC microgrid and there's a failure from the grid side also, then also this because of this local generation we can supply our load. So that's a like we do not require to lay down an emergency line for for maintaining the proper quality of power to the load. So if you see the architecture of a DC microgrid, it's simple. It's being shown as the radial architecture of a DC microgrid. So you can see it is being utility grid is there, and there is a single radial line. On that, many sources are being connected. It's including AC load, DC load, multiple loads are being connected, and there's one single line. And this through converter, this is being connected through the utility grid. So the converter acts as a link between the grid and your DC grid. So suppose anytime if suppose the utility grid fails, then this whole system may act as an independent unit and has to sustain the whatever load being there in the localized unit. Okay. Another aspect that we can see, instead of radial system, we can also have ring architecture of a DC microgrid. Like in a radial line, suppose if there is a fault at one location, you will see that if suppose one fault is coming in between the DC grid, then whole unit may be get disturbed. But suppose if you are having a ring main system like this, then if suppose any fault occurs in a system, then we may isolate using intelligent static switches, and the rest of the loads can be catered easily. So this is another architectures that that people thought of for a DC microgrid, that is ring main architecture. Okay, so one important question here comes: what should be the voltage level at the DC grid? So it depends. Like suppose as per the standard, generally 380 volt and 48 volt are two different standards for low voltage side. Basically, I'm talking about distribution side. For 380 volt DC grid and 48 volt DC grid. Basically, 380 volt is being kept as a standard. Reason is that a single phase can be integrated easily at this 380 volt via your power electronics converter. So basically, you can see in a radial architecture, this converter, if it is connected with the single phase line like 230 volt, then it can easily connect it with 380 volt DC bus. So this is on the standard. And for feeding the local loads, like nowadays we find so many appliances that is based on DC itself. It's not required to plug into 230 volt. It can work on the DC. So 48 volt DC is the standard that is being kept for varied types of load, like refrigerator, light load, and very consumer loads are also compatible with 48 volt. Nowadays we are having EV chargers, that's your e-rickshaw, that is also being charged at 48 volt. So this is one standard that people think of using. So if you see the control part, basically this microgrid is the control basically divided into three parts. One is primary control, secondary control, and tertiary control. So primary control, it means that we are talking about the converter level control. Okay, so basically this is primarily being used for current and voltage regulation via power electronics interface. But whatever demerit, we'll see in the few course of the slide, that we are going to face some issues with the primary control. So that's way we have to go for a higher level control, that is called secondary control. Basically, this secondary control and primary we can say they are independent, but they have to work together. And that too, this control is going to be governed only through the power electronics converter. Okay, so basically, secondary control will help ultimately to restore the voltage and power quality enhancement. And this tertiary control basically used at very top level for power management. Basically, in an area, not to be only one microgrid, you can have different microgrid that being connected with the grid. So we require a master controller that will take care of the whole power that being produced in the microgrid. So if suppose a microgrid requires some power from the outside, or if there's excess power, it requires to send it to some other location, this tertiary control will take care of the overall power that is being circulated inside the microgrid. Okay, so in our discussion, I'm going to mostly focus on primary control, and thereafter we'll take over to the secondary control. Okay, so if you see the aspects to be checked by appropriate control in a microgrid, basically we want to go for bus voltage maintenance, like the common DC bus, how we'll maintain the DC bus voltage to a value that we already predetermined, the reference voltage. Thereafter, load sharing around the parallel sources. Like you know that in the radial feeder line we have seen, and the ring main system, like we are not going to have a single source that being connected with the DC microgrid. We can have a multiple number of PV panels that being connected to the common DC bus, or we can have a battery, PV, all are being connected. And reason that we can't have all the sources with only PV, or we can't have sources with only battery, because we want to make the system to work in a sustainable manner. Okay, so suppose if we are having a photovoltaic system, photovoltaic is a current source and that too intermittent in nature. So obviously we require to have a backup with the battery. So in the system, in the concept, I have considered here two different voltage sources, and how these two voltage sources, they are going to be integrated with each other in a common DC bus. Okay, so and I have not considered it being connected with the grid. Okay, so if you see the general block diagram of normal, if I say that a single DC source is there, and it being interfaced with some DC-DC converter. Particularly, I am taking here a boost converter. It can be buck, boost, whatever it's the requirement. Suppose if I'm using boost converter here, okay, so if suppose a single source is there, okay, and here I have assumed there's a line resistance is 0, that whatever output is there from the converter, ultimately it is going to be connected with the line. Okay, so suppose you are having load at some distance and you are generating a one station, and there is a suppose a 500-meter distance is there. So obviously the line is going to have some resistance. So here for our discussion, I have considered this resistance to be 0 for the time being. Later on we'll include this resistance and we'll see what is the impact on the performance of this converter. So suppose if I'm having a DC source and it being connected with a boost converter, so based on its control, I have just used a simple outer load voltage control. You can see you just keep one reference voltage and actual voltage that being compared, and error is passed through normal PA controller, and it will generate a duty cycle to have a PWM. So it is something like this. You can see at the bottom, PA controller is basically compared with a carrier wave in the comparator to generate the duty cycle. Okay, so this is ultimately going to control by converter to make the common DC link to a reference value. Suppose if I am taking this VDC as a reference as suppose 250 volt, through simple voltage control we can have this voltage to be fixed at 250 volt. So far very good, no issue. Okay, now moving ahead, we can have this we can have this inner and outer loop control also possible with this normal boost converter. So here basically we are going to embed one more loop that is called current loop. So basically we can also use the voltage current loop, but if you are embedding the current loop, what with the advantage we are getting a protection in the current also. Like we like at any point of the the converter won't be giving a higher amount of current. So this current loop is also being embedded for a protection against the current fault because of high current. So it will never happen. So here again we make the VDC again 250 volt according to this voltage loop. As again it's a PI controller, it gives a reference current that has to be maintained through this boost converter, and it is compared with the actual current and it's passed through its PI controller, and again it's give a duty cycle that is comparing with the carrier to generate the gating, and accordingly it will maintain the DC link voltage. So there is no issue with if I'm having a single boost converter fed through DC source, we can easily maintain the DC link voltage at a constant value with voltage control loop and with inner outer loop control method. Okay, so based two methods you can use. Another like current control loop, if you are embedding, you basically you are like gives extra protection to your converter against any short circuit fault also. But in this condition also I will assume that there is no line resistance. So moving ahead, now if we are seeing, if we just try to connect now two DC sources to a common DC bus via this DC-DC converter, again the boost converter I am using. So if you are having two converters connected to a common DC bus now, and it is feeding a common load. So now if we are assuming that these two DC sources VDC1, VDC, all are having same rating. Suppose if they are of the same rating, converters are also the same rating, and again I am assuming this line resistance to be 0. Practically it's not there, always there will be a line resistance. Here for some explanation I have assumed this line resistance to be 0. Now we are having a common load. Now as we have control our individual converter in a similar manner, if I am controlling these two parallel converters, what is going to be the outcome that we see? So suppose I have now applied the same controller as we were doing with the individuals. I have just assumed the reference voltage as suppose 250 volt. For individual terminal voltage V01, I try to maintain 250 volt. Here since these line resistances are 0, so this VDC and V01, VDC and V02 all are same only because I have assumed this line resistance as a 0. So keeping this reference voltage as 250, I am comparing with the original voltage. Error is passed through PI controller and it gives a duty cycle that will give command to my DC-DC converter to generate appropriate pulse for throwing the power, or you can say to maintain the voltage V01 as a 251 and V02 250. Okay, so basically using this control, we are going to maintain our voltages as per reference 250 volt, and there won't be any issue. So this question, is this control going to work? Yes, definitely it will work, but I have assumed very few things like the condition that all the line resistance I have assumed as a 0, and the controller is set to be referenced at 250 volt for each converter. So I just given the data. Basically I through simulation, whatever the value I got, that's I presented at the bottom. You can see cell number 1, this VDC, sorry, this would be VDC1 and VDC2 actually. Okay, so these two voltages VDC1 and VDC all are kept at 100 volt. Line resistance I assume 0. So based on this, current for individual converter is coming as 6.3 ampere and 6.3 ampere, and total is coming 12.6. So you can see both the converters are feeding equal current to feed to the load 12.6, and the voltages are kept as reference value as 250. Okay, so and the common DC link voltage is also 250 because I have assumed the line resistance as 0. Okay, see the third condition that I marked red. If suppose other DC link voltage gets up, okay, initially in serial number 1 and 2 I assume that two DC link voltage are same, but suppose if I am having a one DC source to be higher than the other DC source, what will happen? Is the sharing again is going to be uniform? Obviously no. You can see through control, even now V02 and V01 will try to maintain a common voltage of 250 volt, but since the DC voltage is the input DC voltage of one DC source is more, the sharing by the DC source having higher voltage is more. Now it is not uniform, it is different now. So you can see I01 is 4.9 and I02 is 7.5. So it means that those, if we are applying this control, then this control will verify when we assume line resistance is 0, and it will have the uniform sharing of power only if they are having equal, like they are having voltage source to be of equal value. But suppose if one source is getting higher, then the power transfer from the higher voltage source is going to be more, or it is going to control the DC grid. So suppose if we further increase the voltage of VDC2 to higher voltage, then the DC microgrid voltage will be fully controlled by the DC source. So it is simpler, like if suppose in a generally in a power system, the PCC voltage, or you're talking about the grid voltage, is going to be maintained by the grid. And if a DC wants to insert, it will insert as a current source. It will never try to perturb the voltage. It will just respect the grid voltage. Similarly here, if you're having two sources and one source is powerful enough, then other has to accept that. So that is happening here. So if VDC2 is of higher voltage or higher power rating, the VDC1 will go down. It's getting down, even though it has capability to transfer the current, but it is not able to do so because of this present control. So far it may work. There is no issue, but the problem with sharing will come when one source is having the higher value or higher current rating. Now here, same converter, same two parallel converter. Now I inserted a small amount of line resistance that initially we considered that there is no line resistance being connected. So now if we are connecting this line resistance, now the question is this converter is going to work again, working very fine as with this conventional control? As we did last time, this is going to working very fine with the assumption that this line resistance are 0. But is this parallel converter with the conventional control is going to work fine with if I am including this line resistance? For simplicity, just I am included this line resistance of first converter only as 1 ohm. I just considered 1 ohm as a line resistance. Okay, and for other converter, I have considered the line resistance to be 0. Now, whether this control scheme is going to work straight away? No. Why no? Just see. If again with the same conventional control, if we try to maintain the terminal voltage V01 and V02 as 250 volt, okay. So suppose if I'm saying that for converter 2, if I'm trying to maintain this V02 as 250 volt and this line resistance is 0, then what is going to be common DC link voltage? Obviously there is no line resistance, then V02 is going to be equal to VDC, fine. So suppose if it 250 volt, then again 250 volt going to be the common DC link. But if suppose if V01 also going to be controlled as 250 volt, so if V01 is 250 and here again the voltage is 250, so what is the power transfer from this converter 1? Obviously there is no potential difference, so obviously there won't be any power transfer. So it means that under this condition, if we are using this conventional controller, then first of all, and this is going to always the practical case that we never have the line resistance to be 0. It's always going to have some value. So this controller will never deliver power, or if this controller is not going to work effectively, it will like the error is never going to be 0 if I using this converter with line resistance. So if you are having line resistance, if you consider in a system, that is always practical case, the parallel operation is not going to work with the conventional voltage control loop or with the normal voltage and control loop. as you can see, the sharing power from the one source is getting down or is going to be zero straight away. Okay, so it means that so whole control of power is basically governed by the second DC source. So you can see here the sharing. You can see the simulation results I have just tabulated. Again, sorry, here this should be VDC 100 volt and VDC 2 again 100 volt. Two voltage sources I have taken. Again, I consider line resistance as 1 and another line resistance 0. So you can see I have especially marked red. The sharing of I01 gone down to 2. Okay, like you can see that last time when we are discussing with 100 volt and there was no line resistance, with the same controller there were equal sharing of power, and this was sharing 6.3. We were getting total current at 12.6 to total volt, and it's able to maintain a DC link voltage as 250. So we're working very fine. But now you can see just by incorporation of simple line resistance that is going to be always there in our system, the current sharing is going to be totally uneven. Now with this uneven power, you can see that this I01 is 2 and I02 is 10.5. It means that though they are of equal rating, though they are of equal voltage, then also because of line resistance that is not a part of DC source, that is line resistance is not a part of your converter, but because of the line resistance, even with the same control, the sharing becomes uneven. So what happens? One converter is going to be at very light load and another converter is going to be at heavier loading condition. So here one will be heated up, and because of excess power, like I'm saying, this extreme condition, what may happen if suppose RL1 is going more and more, suppose it's getting 2, RL1 is 2 ohm, then what happens? Finally, it may happen that full current, whatever load requirement is there, it's going to be shared by the converter 2 only. Converter 1 will be relaxed. So high current being passed through a converter 2, it may destroy the converter itself. So this conventional controller is not going to work in a practical scenario if we consider the line resistances. So what is the solution? So solution lies with basically there are many approaches. So the major approaches are based on master-slave based control scheme. Okay, so master-slave control scheme is that one will make one as a master and other sources as a slave. Like in normal power system, we treat grid as a master, and whatever DCs are there, like your photovoltaic, your wind, your battery, these are all going to be in the slave mode. Okay, so basically master is going to be in the role of voltage source. It's maintaining the voltage at the common DC grid or the PCC you talk about, and the slave is going to respect that, and it will be in always current control mode. But in this, you require high bandwidth communication, like you require information from all the sources. Okay, like that you require a full communication. Without communication, this is not going to work. And that communication high bandwidth, it means that the communication has to be very, very fast, because the power electronic switches that we are going to control using this DC-DC converter is going to work in kilohertz range. Okay, so you require to like accomplish your communication in microseconds. So obviously you require a higher bandwidth for your control purpose. So master-slave configuration is very good. It's easier to have the one master and other as a slave. But thing is, high communication bandwidth is required. So laying of communication line and optical fiber, this is going to incur a extra cost in the microgrid. Another control is basically nowadays it is being used is Drupe-based control scheme, and that Drupe-based control scheme is without, first of all, major advantage is without any communication from the neighbors. Okay, so it is without interconnection, high bandwidth communication is required. it is more suitable with the DC microgrid. Like just I have taken one definition from Wikipedia. This is droop-based control. As we know, for our conventional utility, what is this? Basically, it is control mode used for AC electrical power generators, whereby the power output of a generator reduces as the line frequency increases. So basically, we were using this droop scheme in our normal, in the normal grid system, where we are having a number of synchronous generators are being in parallel, they are being connected, and without any communication, they are able to share the power. And that too, what is the basis of that? That is based on the droop only. So basically, the droop-based control is being utilized long back, and it is utilized in the synchronous generator system where they are sharing power, okay, based on the droop. Basically, if I increase the frequency, if suppose if grid frequency is increasing, so basically it demands that the power output has to decrease it. So F by P curve is there because basically that's droop is being defined to decrease the power as per the frequency. So a similar type of concept can easily be applied for DC microgrid also, because since you have seen that what is the problem here in our conventional system with conventional control, that even if there is a line resistance, we were trying to maintain the terminal voltage of each converter to be at constant 250 voltage. So what happens if we are making 250 volt this converter also, converter 2 also, and converter 1 also, and both are acting in a master mode, then what happens? One will be getting down because there's a line resistance being incorporated. But suppose if both the sources or both the converters has to share the power, then what we can do, a simple logic is that if we can anyhow able to droop this voltage in this condition, like if I say that if a normal power in a normal electrical circuit, if suppose in a normal electrical circuit, if I increase the resistance, what happens? Basically the current decreases. So current decreases. So if you want to have a same gradient of current you want to push, then what you can do? You just have the gradient, you maintain the voltage. Like you decrease the voltage or terminal voltage, V01 or V02, obviously you will have the gradient from the converter and you can push more amount of current. So basically droop is being used to decrease the voltage with as per the current that is being passed through it. So suppose in this converter, you can see in this converter you are having converter 2 is sharing more amount of current. Okay, so if we sharing more amount of current and there is a small droop is being like any droop you take it, then if there's a high amount of current, it means that chances of having more droop is there. Okay, so you can see now if we see the droop control for two parallel converters in a microgrid, how is going to be? Basically, we are making a curve V versus I, voltage versus current for two different converters. Like the here I have taken slopes. Okay, these two slopes may be same, may be different. Basically, it depends upon the what is the rating of that converters. That converter rating might be same, converter rating might be different. It is similar to your generators that being connected with the utility, that generators might be the same rating of the different rating. So accordingly, the droop curve is going to be defined. So based on droop curve, okay, so this you can see this droop curve is basically decided by the ratings of that converter, and based on this is going to give you some value called RD1 and RD2. This is a droop resistance we say, and these are all virtual resistance. This RD1 and R2, these are all virtual resistance. Basically, this is not into a part of your actual line resistance. These are that we have seen, these are line resistance. This is different from your RD1 RD2. This is a virtual droop resistance that we are going to incorporate in our system. So initially we were keeping this reference as a DC link as a VDC. Now based on the current that we are going to derive from each converter, we are going to provide some droop. delta VDC, as you can see. And overall, they are going to arrive at a particular reference voltage that they are going to try to maintain it. Okay, so based on this, now if we see like whatever converters we are discussing in the parallel operation, now again same converter, same control operation, you can see one extra loop is being embedded, that is called droop control. Okay, so here I have incorporated one droop here. So what is there? One I01 is there, basically that is output current of the converter 1 is going to be multiplied by the droop resistance. So basically I01 into RD is going to be a voltage. Okay, and basically this is going to be subtracted from the common DC link voltage. So what is the common DC link voltage? Suppose if you try to maintain as a 250 volt, so we are just going to subtract this 250 volt from the droop value. Okay, so you can see here, if suppose VDC is 250 volt, so this delta VDC basically it is given by RD into this RD1 into I01. So we are subtracting this droop value from the reference voltage. Okay, so now what is the resultant now? Now we are not trying to maintain 250 voltage. Now the voltage is lesser than the 250, is 250 minus the droop. That's given by I01 into RD1. Remember this RD1 is actually a virtual resistance, it's not a resistance being connected. So with this we are basically getting a lower reference DC link voltage. Okay, now we are going to compare with the V01, and again we are applying two control loops, voltage control and current control loop, to control my converter 1. Similar for converter 2 also, we are applying this droop I02 into R2. Basically we are making a voltage. So here this RD1 and RD2, these are your virtual resistance that being connected for droop, and this values could be same, could be different, could be lower value, could be higher value. That is the challenge. Okay, so we'll see what are the challenges for this selection of this droop resistance also. So you can see by incorporation of this droop resistance, basically you are reducing the terminal voltages. So if I am able to reduce the terminal voltage, so obviously you are getting more gradient to transfer the power in spite of having line resistance, because in practical case we are going to have line resistance. Once there is a line resistance and we want to push the same amount of current, then obviously we have to have the high gradient. There should be more potential difference. So how we can have the more potential difference with respect to input voltage source? Only methodology is that we decrease the V01. Okay, so by using that, basically we are making a condition so that there should be uniform power sharing from DC1 also, or VDC1 also, and DC2 also, uniform power sharing. Because if we are not applying this droop, there won't be any sharing. There will be non-uniformity in the sharing, and one converter might come under high stress if we are not incorporating those conditions. Okay, so first thing, is this control scheme is going to work? Like previous time, we have seen that with the incorporation of line resistance, normal voltage and current loop is not going to work. Your PI controller is going to always in saturation mode. Your system will be out of control. So by using this droop control, basically without communication, we are able to control our converter in such a way that they share uniform power through each converter. So first I assume this droop resistance as 3 ohm for each RD1 and RD2. Okay, these are your virtual droop resistance that I assume this to be a very low value, 3 ohm only I have connected 3 with. Okay, so even with the incorporation of droop, current sharing is not uniform for equal rated sources, and sharing affected with change in line resistance. Now just I have tabulated one result. You can see this VDC1 and VDC2, I have assumed again as 100 volt. They have uniform rating. Here, I have just assumed that this RL1 as suppose 2 ohm, and RL2 I have assumed 0. Again, I have assumed this is 0 only. Okay, then you can see here now with I have say just see the serial number 2, where I have just again considered the line resistance as 1 only. With the incorporation of this group resistance RD1 3 ohm, RD2 3, then current sharing IC1 is 5 ampere and IC2 6.46. Okay, and both having both were trying to maintain the DC link voltage as a like V01 as a 234, and this V02 as a 229.7, and this common DC link voltage should be again this equal to V02 only. It should be 220, not 250. Sorry for that. This VDC should be 228, and the second condition is 229.7. So now this common DC link voltage is not 250 volt, it's 228 and 229. Okay, so you can see if you compare this with the conventional control without drop, this I01 with the same line resistance you were having 2, and I02 was suppose 10.5. Now with the same converter with application of droop control, now we are having I01 current sharing increased to 5, and I02 again decreased to 6.46. Now they are having, again it's not uniform. Again I'm saying this is not uniform, but the performance has enhanced as compared to the normal conventional control where droop is not being applied. Okay, but again with smaller droop you can see there's still, even if they are of equal rated condition, there's a difference in the current sharing. Moreover, there's a high decrease. 1 second, I should decrease. This value is actually it should be 228 and edit it, otherwise we will create confusion. Okay, so this should be actually 228 and 229.7. So you can see what is the advantage and disadvantage you are getting. With the conventional controller, you are trying to maintain 250. So anyhow, you were able to reach 250 volt in the conventional controller without droop, but it was not working actually. But here in the droop, everything works fine. But even though you are giving a command to make to VDC to be 250 volt, but actual DC link voltage that is coming out to be 228, and if I having more amount of line resistance, that is further decreasing. Okay, so even with the incorporation of droop, you are seeing that from the result with the lower value of droop, if the sharing is not uniform, and with the incorporation of droop, there is a decrease in the DC link voltage also. So suppose if we want to improve the performance of this droop control to have the uniform sharing of power even with the droop control, what we can do? Okay, so for that we just we make a suppose for two converters, if you make a equivalent circuit diagram. Okay, so normal I just make a equivalent circuit diagram for parallel DC converter with incorporation of your droop resistance. So basically this V0 that you can see here, V0 star, is basically this reference voltage that you try to maintain as 250. This RD1 is been incorporated as a virtual resistance. Actually, this is not resistance of the line resistance. This is a virtual resistance that I have connected. So V01, V0 star and RD1. If you subtract whatever drop is there, you will arrive at the V01, that is the terminal voltage of one converter. Similarly, for converter 2 is V0, again the same reference voltage I have given. So same reference voltage, and they will Again, line resistance is you can have the same line resistance or you can have different line resistance. That's assumptions. So and these two converters in parallel, they are feeding a common load. Okay, so if you see these two converters, basically they are two converters feeding to a common load. So we can have small equations that we can model this two parallel converters, and we'll figure out that what is the V load, because from both the side the voltage has to be common, V load is common. So simple, if you apply the KVL, you can get the V load as V0 VDC. Basically it's V0 star is basically VDC, common DC link voltage. That's reference I want to maintain, suppose 250 volt. So minus I01 into RD1, drop across this virtual resistance, minus I01 into line resistance. So you will arrive at the common V load. Again, this for second equation also you can do it from the right hand side using applying the KVL. You will arrive at 1 and 2. So since both the V load has to be same, if you simplify 1 and 2, you will simply got the equation like you will get a relation between I01 and I02. That's basically like how much the power is going to be shared by I01 and I02. What is the current sharing? Okay, so if you see the current sharing equation, so I01 by I02 is given by RD2 by RD1 plus some expression you got here at this point. Now, with this equation number 3, if we see that there is no line resistance, if I assume first, that if I assume that initially we were assuming in the converter there is no line resistance. So if I'm assuming there is no line resistance is being connected, so simply you just put R line 1, R line 2 to be 0. So you will arrive at simple equation. You can see here, this without line resistance, the sharing of the current is inversely proportional to Drew resistance. So it means that if we are having if we suppose there is no line resistance and you are applying the Drew, then based on the Drew value, that is virtual resistance, you can have this current sharing. So suppose you're having one converter of suppose 2 kilowatt, another converter is 5 kilowatt. So if you want to share according to this power, okay, then you accordingly you need to put the Drew resistance value to share the power at a uniform rate. Uniform rate is as per the rating, okay, because a 5 kilowatt can share 10 ampere, 2 kilowatt may share 5 ampere only. So based on the Drew, based on this simple equation 4, we can basically apply this in our controller in the boost converter. Now, with line resistance, suppose if we incorporate the line resistance in the system and we want to share current inversely proportional to virtual resistance, like you see here, one important aspect I forget to tell. In this, when we are incorporating the virtual resistance, then you can see the cell number 1. There's a line resistance I have included. I especially mark as red. You can see if I'm with the same Drew value, 3 ohm only, if I'm changing the line resistance RL1, suppose initially it was 1, now if it is kept at 2, then you see the current sharing. Is it same? No. It means that even though you have incorporated the Drew, if we change the line resistance, the current sharing gets increases or decreases. So it means that this current sharing is not going to fix it. Its value is going to be always changing with respect to change in the line resistance. So do we really want to have a current output from a converter that is not in our control? No, it's not feasible for a controller designer. That we always wish to have a control in such a way that whatever we predict, that should always be there. Otherwise, if line resistance is changing, you will have a different current. So that is not practical scenario. So we want to devise a control in such a way that even though there is a change in the line resistance, there should not be much change in the current sharing. Okay, so you can see, so that you can realize from here that seeing the equation 3, okay, if we incorporate the line resistance, okay, and then also if we want to have a current sharing, same Okay, same inversely proportional to virtual resistance as equation 4. Okay, so basically we want to maintain this equation 4 even though if we are having a line resistance. Okay, this is my major like point, that I want to maintain equation number 4 always. Sorry, I want to maintain equation number 4, means current sharing inversely proportional to group resistance. So what we can do, basically, if we see the equation 3, if we can have this ratio of group resistance as R line 1 by R line 2, okay, if we can substitute these values, it means that whatever line resistance are there, the ratio, accordingly the group resistance ratio should be there. If we maintain, if you put this value of equation 5 in 3, you will get automatically this I01 as inversely proportional to this group resistance only. So it means that with this we can have this. It means that whatever proportion is there in line resistance, if we try to maintain the same, you can curtail the differences in the power sharing. So one more aspect you can see here. So we are just initially I just kept this value, group resistance value, as a 3. Now suppose if we want to like suppose see the effect of increasing the group resistance value. Okay, so if we increase the group resistance from 3 to 40, okay, I have just increased the group resistance value. So what is the impact? Now you can see I am having the same converter, same control, just I have increased the group resistance to from lower value to higher value. Now again same, see the result, whatever we were discussing the result there, see the result here and try to compare. Again I'm showing the result at that time. You can see the with group resistance with 1 ohm line resistance, you were having current sharing as a 5 and 6.46, and you were having that common DC link voltage as a 229.7. now with this, see it with 100 ohm, okay, so basically this should be VDC1 and VDC2. Okay, so this is VDC1, VDC2, 100 volt, and line resistance as 1 ohm. You just see the current sharing now. It's uniform 3.06 and 3.14, very close to uniformity. Like they are, since they are of equal condition, then sharing should be equal. But because of line resistance, what happens? There was a non-uniform sharing in the current. But now you can see with the higher group resistance, the current sharing becomes uniform. Okay, so it means that with incorporation of line resistances, if we want to have an uniform current sharing, then we can do it by enhancing the group resistance. Okay, since if you're having higher virtual group resistance, obviously it will curtail the effect of your line resistance. Okay, so with this control, what basically we are doing, we are able to maintain the current, informed current. Okay, but what is the sacrifice that we have to make? You can see here, see the voltages V01 and V02, this comes to 127.2 and 124.2, and the common DC link voltage of circuit, especially now it is coming 123.7. Just start with the very basic. I told you that initially the boost converter, common single DC, the boost converter will try to maintain a voltage of 250 volt. Now if we are applying the group control to get the informed power sharing, now we come to a DC link that is very low, 123.7. so now we are sacrificing the common DC link voltage. So you want to, like, if the objective is to have the informed current sharing, then you have to sacrifice with the DC link voltage. So that is the major disadvantage with the primary control, that people used to have this with the group control, and generally without communication people used to work with the group control. But this is the major disadvantage, that they are able to achieve the current sharing very good, but they have to sacrifice with the voltages. So what we can do, so I think this primary control is not far enough for maintaining both informative current and for maintaining the DC link voltage to a reference value that we were desired to have around 250 volt. Okay, so what we can do, solution, obviously we have to go for the other control, that is secondary control. So basically first one is the primary control. Okay, so there are like here when just I have assumed that I have increased the value as a 40, okay, to have the current informed sharing, but problem is that we will having arriving at the very low DC link voltage. But you can't just directly fix the value to 40 or 30 or whatever, no. So we have to fix an optimum value of the droop resistance. So there are adaptive droop controller also. Like how do we like lot of research will find papers based on this adaptive droop, deadband droop, nonlinear droop. Like droop value is keep on changing based on the condition. Okay, like suppose the line resistance is changing with the changing the temperature. Other accordingly, the droop has to be adaptive so that the shearing has to be uniform. So you'll find a lot of research papers on adaptive droop, deadband droop. So these are advanced control that being devised in the primary control also to get the optimum result. Okay, so a lot of research you'll find there. Another control you will find for that is secondary control that we are more interested now. The primary control, you know, that's what is the problem, what are the issues. So we'll go with the secondary control. So under secondary control, you'll find basically centralized, distributed, and decentralized control. Okay, so under distributed, that is basically nowadays of interest for most of us is distributed control, and that is cooperative and non-cooperative. Okay, so non-cooperative means it means that it is basically using average current, average voltage, DC bus signaling. So dynamic consensus, different methodology for cooperative. Because you will find a lot of papers and like research you'll find on dynamic consensus method, your multi-agent system, consensus method. These are the different secondary control, advanced secondary control people are thinking to apply to like get rid of the problem that people are facing with the primary control. Okay, so if you see the centralized control, basically we apply the primary control. We were knowing that what was the problem. Problem was that your common DC link voltage was not able to reach to the optimum value of 250 volt. Okay, so we require another controller that gives the command to boost the reference voltage so that we can reach to the reference value. Okay, so basically this secondary control will compare the voltage to the reference voltage. Like suppose 250 volt, it will compare, and what is the actual voltage you are getting compared, and the error is going to be passed based on the controller output to the all primary controllers. So whatever information secondary control is giving to all primary control. Okay, so in centralized controller there is a one link for secondary control. Okay, and all are giving information. Like secondary control is taking the data from the common DC bus, accordingly it is giving command for all primary control. So problem is there, if suppose this secondary like anyhow this central controller is not working, then the information that is received by the primary control is not getting, then the whole operation will malfunction. Okay, because it's a single point failure is there. One point will fail, others will automatically it will fail only. So that's why this the centralized control is very easy. Basically, it can be controlled very easily. Like it's very cheaper also. But problem is only with the that basically the chances of failure is more in the centralized controller. Now coming to the like distributed control, here basically each primary control, okay, is going to be getting some information from a secondary control. Again, it's getting a control from secondary only, but here the information is going to be I think this is the problem with the diagram. Okay, I will just leave this. Okay, so basically in the if you see the centralized control again, here you can see same converter through parallel converters are being connected. Okay, so the secondary controller is basically comparing the actual voltage with the reference voltage of the DC bus that you want to maintain, and this is giving a error in voltage, and that error voltage is basically is basically compared, is being added with the reference voltage. As you know that we were maintaining this V01 as 250 volt, and we were not using this initially. This delta V control we are not using at that time when we were applying the droop control. Okay, so here this information delta V now is coming from where? From the secondary control. Now this delta V is going to be added with this V01. Okay, thereafter again this is the same primary control. This part is the primary control part, this part is the secondary control part. Okay, this delta V part. Okay, so it means that because of these two, your basically the voltage gets decreased. Okay, so now to enhance the voltage in the DC link, a secondary control is giving information based on the error and the controller that how much voltage we need to add to enhance the common DC voltage to a reference value, or the reference value that we targeted to achieve that. Okay, so same you can see here for the second converter also. Again, this is the same primary control part. Okay, now the primary control part is being added with the delta V part. Okay, so it means that in the centralized control you can see that all primary control, okay, for each converter is sharing the same delta V. Okay, so suppose if anyhow this information fails, or there is no information from the delta V from secondary control, then what will happen? Like the link is going to fail automatically, because this is a central point of it. Okay, so that is the disadvantage, and the advantage also with the centralized control. But if you talk about the distributed control, basically distributed control, we are taking information from all, and accordingly, like we said, we are going to have different nodes. Different nodes means that for each converter there is going to be information of voltage, current. So you can have an n number of voltage like converter that is having many voltage and current is like current. So basically, secondary control is going to have information from all the converters. Okay, like all the information about voltage and current. Okay, and based on that, basically it is going to give command to individual converters. Okay, for individual converters the control is different. It's not going to be same as in the centralized controller. So this central controller is basically what they're having up all the information from all the converters, and this secondary controller is going to give command to individual primary controller what to do. So even if the control for one converter is missing, others can work fine. So that's why the failure chances is less in the this distributed secondary control. So basically what we are going to do here is look into that. Here we are having two DC links that basically we want to maintain. Okay, that is basically your VDC1 and VDC2 I took. Thereafter, basically you are having two terminal voltage, V01 and V02. Okay, so now we are going to make an average of this. Okay, average DC link voltage of two, how much voltage you want to maintain. Then this is average voltage. Thereafter it is compared with the terminal voltage of each, and that is going to pass through PI control to give a delta V1. Here also for the secondary for the second converter also, you are going to have some DC link voltage VDC1, VDC2. This is some we are going to make an average that is going to be compared. Okay, so basically here what we are going to do, basically we are VDC1, VDC, the actual DC link voltage that you are getting. So you have seen that from the result you can see this V01 and V02. These are not they are not common. They are different values. So what the primary control is, secondary control is doing, they are taking information from for the V01 and V02. Okay, so they are having some information like this voltage different. So they are making average of these two voltages. Okay, and they are comparing with what is the reference voltage. Okay, so what is reference voltage? We want to maintain. Suppose in this case, I am talking about to maintain a 250 volt. Okay, so here this VDC1 and VDC2 basically is actual terminal voltages. That's going to make an average, and that is being compared with the actual voltage that we want to maintain, and that passed through the PI control. That's given like what voltage we need to add in the primary control to achieve the set target. So now you can see that for each converter there is a different voltages. This delta V1 is for first converter. Similarly, delta V2 is going to be for the second converter. Okay, so since the voltages, the term, because the line resistances of two converters are not going to be uniform. Okay, like this converter one might be having lower line resistance, other converter might be having the higher line resistance. So depending on the line resistance, the terminal voltage V01 and V02 might be different. So the secondary control is going to provide the boost in voltage, like we say the voltage shifting basically. Basically, secondary controller is shifting the voltage, reference voltage. Okay, so the shifting in the voltage reference for each converter is to be different, is not going to be same. So this converter, like this controller, is going to provide you the shifting in the voltage. So by adding this delta V1, basically we are trying to push the terminal voltage V01 to a reference value of 250 volt. Okay, but here if we are just incorporating this average voltage, this first is average voltage control. Okay, now we can work with the average voltage control also, there is no issue. But remember, if we are working with the average deciding voltage, then what happens? You can see if we are making an average of suppose V01 and V02, 127 and 124, it will be suppose 125. But what is the actual voltage? Actual voltage was 127. But you were controlling with respect to average, then the chances of error is there will be difference in the actual voltage and average. So that error, if you want to even minimize, so what we can do, we can have the extra control, that is current loop also. We want to have the average current to be also uniform. So if we are making average current and average voltage and average current both to work together, then your chances of error in the from the reference voltage is going to be a minimal. So here in the average current methodology, basically again same two converter current, actual current is being taken and is averaged to and compared with the actual current and passed through the PI controller to give the current shifting that we need to provide. Okay, so that is delta I1 is being added. Okay, so basically this delta I1 is going to be multiplied with group resistance sometimes to give the boosting in the voltage, or sometimes directly PI controller gives the delta V to add up directly here. Okay, so basically it's not a current. Okay, it's going to be a voltage component. PI controller is giving a current voltage component only. Okay, since it is a like this output is being derived from the current, that's why it's taken a delta I1. But remember, this is going to be a voltage component only. Okay, similarly we can have with the second converter also. So what is the conclusion? Basically this distributed control is basically enhances the operation for your average control based on average voltage and average current. Okay, so like if you see the research part, that I have just covered this average voltage, average current, but you will find there are different methods you will find nowadays that being used to enhance the performance. You will find that there's some control that is based on average droop resistance also, how to adapt the droop from the secondary control itself. So it's going to have the information of the droop of all the converters. Accordingly, they will give the optimum optimum value of droop that we have to devise for to be applied for this control of the converters. So basically, this distributed control basically enhances its performance. Okay, so if we conclude, this DC power systems is basically more reliable as compared to AC. Foremost reason that easily we can integrate our different sources that is DC in nature. Moreover, this DC power systems do not require multiple conversions that because most of our loads nowadays are DC in nature. Okay, and most important factor, you will find that if you are having AC system, then there are harmonics issues, power quality issues. There are many protections that we need to devise. So those problems is much more minimized in the DC system. Okay, like we are talking about unbalancing, so many issues you will have with the AC system or AC microgrid also. But you won't find those things in the DC. DC is like reliability is getting higher, so that's why it's like people are getting more attention towards like creation of DC microgrid or creation of DC homes. They try to satisfy the power requirement of local community through DC power itself. So this is going to help a lot for in the near future. And this we can apply this droop-based primary control device with the secondary control will help to basically it's helping to improve the performance. How? By enhancing the like DC bus voltage to a reference voltage. Okay, like whatever the demerits that we are having with the primary control, okay, those things can easily be tackled with the secondary control. Okay, so basically nowadays the primary control and secondary control are embedded in one control itself. Okay, so they are working in hand to hand, so they are not separate control. But if you talk about the tertiary control, that is basically used for communication between two microgrids. Okay, so if you want to have a communication with one microgrid to the other microgrid, this tertiary control is being used for power transfer. So those things for secondary, for tertiary control. Okay, so thank you all for patience sharing my short lecture. Okay, so if you have any question, please.
Hello, sir. So thank you for your session, sir. Now let me share the questions which are there in the YouTube, sir.
Should I stop? What is difference? What is difference? Slave-based and droop-based control scheme. Okay, so basically, Souvik, can you hear me? Okay, so in masters, there are two configuration I talk about. One is master slave, and is droop. Two things are different. Okay, like master means that we assume, like if I can give the example again with the power system, you will acknowledge it very easily. In the normal power system, okay, the grid is assumed to be a master. Okay, master means who will be the controlling the DC link voltage. That is the main major issue. Okay, now if you're having a master as a grid, then the grid voltage we assume as a fixed at 230 volt or 415 volt. And whenever we are trying to integrate our distributed generation in the grid, we assume that DC is as a slave. Slave means first we want, like, the DC has to synchronize with the AC grid. Then with the synchronization, DC has to transfer the current in with respect to the phase in the phase at the grid. Okay, so the slave is not going to disturb the grid voltage. Okay, slave is not in a position to change the grid voltage, otherwise it may destroy himself. Okay, so basically it respects the grid voltage, okay, and transfer the power in a current form. Okay, fine. And in a very in a vague manner, I can tell you, if your area is there, in an area, particular area, we can have only one boss. We can't have two bosses. Yes or no? Okay. So whoever is the powerful, that is going to be a boss. Fine. So boss means it's a master. So basically, in the DC microgrid also, those basically suppose if you are having a system 10 kilowatt of DC and the one DC of only 2 kilowatt, or we can have a DC generator of 100 kilowatt. So we can assume this 100 kilowatt DC as a master, and that is going to be the primary role for maintaining the DC voltages, because that is a master. Others can supply in a current form by respecting the voltage at the DC grid. Okay, and but in the obviously in the group based basically in the master slave configuration, the thing is that you require the information. Okay, that the communication line is required, that how much one has to share. But in a group based control, basically all are master. Okay, and if you are having multiple number of synchronous generator in the system, so how they are going to stabilize the frequency and the voltage? So that same concept is applied in the DC microgrid. Basically, we are having many DCs are being connected to the DC microgrid, and based on the group, they are going to stabilize at one common DC bus voltage without any communication. Okay, so that is your group-based control scheme is there. But you have seen that I showed you that how this group-based control is going to have the effect on sharing of equal current, but has decreases the common DC link voltage. That can be easily sought out by the secondary control. Taking into second question is Ripaka's taking account of output voltage ripple DC source of magnet the converter with less more than will have less OVR, which converter is lightly loaded then. Taking account of output voltage ripple, DC source 1 connected to the converter with line resistance more than second one will have less over voltage, which converter is likely loaded in. No, basically if suppose I have taken two converter 1 and converter 2, okay, so if we are having simple basic electrical, I will explain you. If suppose if I'm having a DC source, okay, and it is feeding to a common load, okay, a fixed load is there. Now it is delivering some current. Now if I increase the resistance, what is the impact on the current? Obviously the current will decrease. Okay, so that basically happening here. You are having converter 1 and converter 2, okay, and I have assumed that converter 2 is not having any line resistance. Then converter 2 is going to have the same voltage as a common DC link voltage. So if converter 1 is also trying to maintain 250 voltage, so what is the potential difference you will find at the two nodes of the resistance? It will be 0. Okay, so if there is no potential difference, it means that there won't be any power transfer through converter 1. So what happens? The load has to be fed in anyhow. So who will feed the load? Converter 2. So it means the converter 2 will be overloaded. Okay, and converter 1 is completely shut down in the very worst condition. Shut down, it means that it's not like that it is not working. It's still the switching is happening, but power, current transfer is not happening. Okay, fine. Okay, sir, any question?
Hello, sir. So that's all the questions from the participants. Thank you very much, sir, for your informative session. Sir has explained in detail on the parallel operation of power converters in DC microgrid. Sir has explained group controls with various illustrative examples with respect to the values of resistance. Then he has taken the advantages and disadvantages of various control techniques. So surely this will help the research community who are working in this area. Thank you very much, sir, for accepting our invitation and spending your valuable time with us. Thank you very much, sir.
Thank you. Thank you. Thank you.
So next section will start sharply at 3 p.m. Thank you all.